Hello, everyone. My name is Brian Rogers, and today we're going to be going over the properties of electrical materials. And so, as part of the honors project, this is to help the students in order to succeed in electrical engineering. And for this specific notebook, we're going to look at the realm of material science and how it's used within electrical components in order to make our circuits. And so we're going to be diving a little bit into the chemistry to look at different types of bonding models. Then after we're going to do a specific study on semiconductors in how this relates to electrical engineering and where we actually use these types of materials. Then, after learning about the basis of why semiconductors are so important, we're going to look at each individual circuit component, the most popular being resistors, inductors, and capacitors. And so we're going to start out with the material phases, and we're going to look at each of these. And so a solid basically does not take on the shape of its container. And so when we're talking about a solid, you can think of anything like, for instance, a brick. And so a brick, it will not change its shape. It's going to remain the same. So you can't put it in something else, like let's say a bottle, a brick won't fit into the bottle. It's going to remain intact, so it's not going to change its shape. And then the next term that we're going to look at is a saturated liquid. And so what a saturated liquid is it absorbs as much heat energy as it can without vaporizing. And so let's look at an example here. So a liquid, we can think of something just like this, like we have some water. Maybe this is in a jar or something. So here's our water right here. And so for water, we have heat energy coming in. So it's going to absorb some heat energy from the sun. So you can think of these as heat waves coming in, and it's absorbing the energy that those photons give off. And photons are just particles of light, photo, which means light. So it's absorbing these heat rays. And so it's warming up. Your water's getting hotter because it's absorbing the heat, but it's not vaporizing. So it's remaining in the liquid form still. So we're still in the liquid stage. Then the next term we're going to look at is subcooled liquid. And so this refers to if a liquid is not saturated, which mean at its boiling point, then it's said to be subcooled. And so you can think of this as when you're on your stove, let's say, and so we have like the little fire right below the stove that is producing some heat, and you have your pot on top. And so right now the pot has water in it, but the water is not bubbling. So we would call this a subcooled liquid because it's not at its boiling point. And so it's there, but there's no bubbles. We don't see anything yet. Then the next term is a liquid vapor mixture. And so a liquid vapor mixture is a liquid and vapor of the same substance that coexist at the same temperature or pressure. So this could be, let's say that we have our water and some of it is in the liquid form right now. So we have some water in our liquid form right here, but we have some in the vapor form as well. And so it might be in the air, some of this water. And so that's what a liquid vapor mixture is it has liquid and vapor particles. So we're going to see the liquid form here, and we see there is vapor as well in the air. So you can sort of think of like in the tropical jungle where you feel it's very moist in the air, but at the same time, you can see water flowing in the river. And so it is both in its liquid form and in the air. So that's why it's called a liquid vapor mixture. They coexist at like the same temperature level. So it might be like 80 degrees or something. You might have some water in the air. It might be moist, and then it will also be in the liquid form, like running down that river. And so Our next term is perfect gas. And so a perfect gas is an ideal gas whose specific heats are constant. And so we're going to look a little more into this later on. Then we're going to get saturated vapor, which is basically a vapor that's on the verge of condensing, is said to be saturated. So basically, if you think about vapor, like we talked about, if there's like water particles in the air, we have our vapor here, the vaporized liquid. So it's in its gaseous stage right now. And so it's on the verge of condensing. And so when it's condensing, that means it's going to turn back into its liquid form. And so that's what it means is it's basically saturated right now because it's on the verge of condensing. And so that's what term we'll use for that one. A superheated vapor. A superheated vapor, it basically absorbs more energy than is needed to vaporize it. And so remember water up here? So we said that it was absorbing energy. And so if it absorbs enough energy, then it's going to turn into the gaseous stage. So it's going to go from the liquid to the gas stage because it get heated up enough and then it can turn into a gas. And so what happens here is basically we still have our arrows that are going in to our liquid, and our liquid gets heated up enough. So our liquid gets heated up enough that it actually starts to form vapor. And so we were able to pass the saturated liquid stage because we got enough energy in order to form vapor. But here what we're going to see is that it absorbs more energy than it needs to in order to vaporize it. So it basically took more than was required to go from the liquid to the gaseous stage. So that's why we call it superheated, because it took in more heat energy than required to start vaporizing it. Okay, now that we talked about those ones, going towards the end here, what did I mean by ideal gas? It basically behaves according to the ideal gas law, which we're going to study here. So you'll see this formula later on, but right now, just become familiar with what it looks like. And then a real gas. What's a real gas? If we're talking about ideal gas, an ideal gas follows this formula. A real gas is basically a gas that doesn't follow this formula. And so if it abides by this formula, that's great. It is basically ideal. But if it doesn't, then it's a real gas. And then a gas mixture. Think of just the name, a mixture. That means like you're mixing things together, right? And so we're going to see two or more pure gases create actually a gas mixture. And so we're going to look at some diagrams where we're going to see multiple elements that might be mixed together. And so what we're going to see here is you can think of carbon monoxide or where carbon monoxide or carbon dioxide. And so if we have CO2, we have carbon and oxygen. And so those are two different types, carbon and oxygen. If we're able to put those together, you would get CO2, carbon dioxide here. And so that's representative of two different elements that are mixed together. So that'd be a gas mixture, for example. Then a vapor gas mixture is basically atmospheric air is one example where we could have water vapor and several gases. So like a mix of gases in the air with some water vapor. So if you think about this, it's just a mixture of vapor, which remember we went from the liquid to the vapor stage, and gases in the air. And so that's what it implies. Now that we talked about that, we're going to look at the Gibbs phase rule. And so let's just try understanding what this is trying to talk about here. And so P here, P means the number of phases. And remember, your phases, you start out with basically your solid. So you can think of the brick, and then you start heating up your solid or So maybe this is your ice cube, let's say. Right now it's solid, all the water. You start to heat it up. So we're heating up our ice cube. And then what happens is then the ice cube's going to turn into a puddle, right? Once you heat it up. So it turns into the liquid stage. And then if you keep applying heat to that liquid stage, it's going to then become a gas. Basically, it's going to vaporize. And so what we're going to see here is it's going to go into the air and sort of make moisture droplets you can think of in the air. And so that would be our phases, the basics of the solid, liquids, and gases. And then F here, what that is supposed to represent is, oops, let me just ignore that real quick. So F here represents the number of independent variables. And so when it comes to working with the material science aspect here, our independent variables in the Gibbs phase rule are 3 degrees of freedom, and they're often referred to as our temperature because controlling the temperature of the room where this is occurring, the composition, so how much of an element mixture you might have. So how much of this element do you want with this other element to combine together? And lastly, the pressure. So how pressurized is this environment? And so those are 3 things that you can try and control within your laboratory setting is the temperature of the room, how much composition of each element that you're going to be mixing together, and the amount of pressure that is in that room. So how much force is acting on it. And so that's what F refers to in the equation, and C is the number of components in the system. And so that means how many things are we actually working with in our system. So let's look at an example. For example, water is stored, so 3 phases are present simultaneously. Okay, so we got 3 phases at the same time. So I know my P is equal to 3. We got 3 different phases. We have the solid, liquid, and gas. Now, we're going to look at what are a number of independent variables? Are we in control of anything here? So are we controlling the temperature? I don't see us controlling the temperature here. It doesn't say that's a degree of freedom. I don't see a composition, like how much water for the mixture, like how much of hydrogen, how much of oxygen. I don't see that here. And I don't see any pressure, basically that they told us. So for a number of independent variables, that would be 0, because I don't see any of these being varied within the problem. Now let's look at C. How many components do we have in our system? Well, we're working with water, right? So that's 1. And so that's the only substance that we have in the environment in this scenario. So we just have 1 here. So plugging into the equation, we had 3 phases. We had 0 degrees of freedom, and we had 1 component. And so plugging that in, now we're looking in the equation 3 equals 3, which makes sense. The equation is supposed to be equal on both sides. And so if we're able to get it to equal the left and right hand side, then that means that the Gibbs phase rule worked and you properly identified everything in your system. Now that we have that, we're going to go to another example. How many phases can exist in equilibrium for a fixed proportion of water-alcohol mixture held at constant pressure? Okay, so right here, let's try identifying how many phases. Well, that's what the question's asking. So we're trying to calculate that right now. Then what about the composition? How many components do we have in our system? Well, it said it was a water alcohol mixture. So water and alcohol, that's 2. And then can we control anything? Here it says we're at a constant pressure, so we can't vary the pressure. And it looks like it's a fixed proportion, so we can't control how much of the composition. But if we're looking at what about the temperature? It doesn't say anything about the temperature. So that is 1 degree of freedom that we are in charge of right here. And so right now, using the equation, we had 1 degree freedom. We had 2 components within our system. Adding these together, I get 4 on the right-hand side, and subtracting the 1 to move it over to the right-hand side because we're solving for how many phases, P. So solving for P, we find out that there's 3 phases that can exist. Now that we covered the basics of the Gibbs phase rule, we're going to look at binary phase diagrams here. And so for the binary phase diagrams, what we're going to notice is that when you're working with elements, they're not pure, meaning that there's not just one element that is within a substance that you might be wearing, such as like a ring. Say, if you have a gold ring, it might be a mixture of elements, actually. It's not just gold. The instrument you're playing. So what we're going to see here, brass, for instance, it basically, what happens here is you're going to notice that brass is a composition of copper and zinc. It's not just one element. In silver is a composition of silver, and there's a little bit of copper in there for your sterling silver. Cast iron has majority of iron and a small percentage of carbon. And so what we're seeing here is that a lot of these items that you might work with every day or use, it's not just one element. It's going to be a mixture of elements. And so that's what we're referring to when we say mixture. It's an alloy. And so what we're going to see is when we have 2 elements mixed together. So this is a mixture, so it's an alloy, right? But it's 2 elements. So that's where the term binary comes in. Binary represents 2. And so 2 elements mixed together. That's what a binary alloy means. And so now we're going to get a little bit into the finer definitions. The majority element in a binary alloy is known as the host ingredient. So this is like your primary ingredient, the main one that you're using within the composition. And then the minority element in the binary alloy, this refers to the alloying ingredient. So you're adding this one. This one is not the primary, it's the minority ingredient. So they like to call this the alloying ingredient. And so now that we know when we have a binary alloy, we have 2 elements that are mixed together. What we're going to form down below is a binary phase diagram. And so you're going to see in figure 2 here from our binary phase diagram that it's a mixture of 2 elements. And so the regions of this equilibrium diagram, which are also known as the phase diagram, illustrate the various alloy phases. So we're going to see for this mixture, it can be either a solid, or it can be in between a solid and in the liquid stage, and it can then turn into just a liquid. And so it just shows that the mixture at lower temperatures, you're going to see if we just have, notice that when we read this diagram, first of all, you're going to see on your X and Y axis how to interpret it. So on the x-axis, it says the composition, weight percentage of nickel. So on the left-hand side, this is 0% nickel, so it's 100% copper. But on the right-hand side, it's referring to 100% nickel, 0% copper. And so that's how you interpret the x-axis. And now looking at our y-axis, it's temperature in degrees Celsius. So 1,000 degrees, we're at lower degrees temperature, and then at the higher temperatures of 1,600 degrees. And so you'll notice the binary alloy, if we do 50% of copper and 50% of nickel, that would refer to this middle tick right here. But if we do 40% of copper and 60% of nickel, what that's going to be is 60% of nickel, because the x-axis represents how much percentage of nickel. And then the rest, the remaining 40% must be the other element, which is copper. And so what we're going to see when we're looking at this diagram is that when you have more percentage of copper at lower temperatures, it will turn into a liquid easier. So that means if we have more percentage of copper, meaning that we're on this side over here, we have more percentage of copper than nickel, we're going to notice you can turn it into a liquid. This mixture can turn into a liquid at lower temperatures. Notice this range right here at lower temperatures. But if you have more nickel per se, so then that means we're on this side of the spectrum. If we have more nickel, it's going to require higher temperatures to turn it into a liquid because you have to go above this threshold. And so that's how the binary phase diagram works. It just shows for the mixture what, based on the percentage composition of each element in that mixture, when it exists as a solid, when it exists as both a solid and a liquid, and when it just exists as a liquid. Now that we covered that, we're going to move on to the gravimetric component fraction. And so this will tell you the weight percentage of the substance. So say we have two substances here. We have substance alpha and we have substance beta. And so we want to be able to determine the weight percentage of alpha. And so what this is going to represent is in the numerator, you'll see x sub beta minus x. And you're probably wondering, what does this mean? Well, x here refers to your composition. And so along your x-axis, what is the composition? How much do you have of substance alpha and how much do you have of substance beta? And so your x is determined by that composition of each. And so right here, x sub beta minus x in the equation, what that is referring to here is it's going to refer to the line over here. And so you're going to notice that it basically went from x sub beta, which is on this side, x sub beta, and it subtracted x, which is this middle point here. And so the subtraction, taking x sub beta minus x, the difference is this line here. And so that's what it represents, what we're seeing. And then in the denominator here, you're going to notice x sub beta minus x of a. And so here if we have x sub beta is at this point right here. So this is our x sub beta minus x of a. X of a is on this point over here. So you would calculate basically the difference. So x of beta minus, so it's going to be this entire line here from x of beta in going to x of alpha. And so that is what would be in your denominator times 100. And so that is going to determine how much percentage of substance alpha you have. And then in order to determine how much percentage of substance beta, what you're going to see in this equation is that you're going to have x minus x of alpha. And so that's going to refer to the line right here from x minus x of alpha. And then all over x of beta minus x of alpha. And so x of beta minus x alpha is the entire line here, because it started from x of beta and went all the way over to x of alpha. And so times 100, that will give you the weight percentage of substance beta. And so that's how you would interpret this diagram in order to determine the weight percentage of each substance. So that's what these terms represent to. The substance beta and then your substance alpha. Specifically, the x is the composition. So x of beta refers to the composition of beta. X of alpha refers to the composition of alpha. And then x here refers to the composition that they describe. So we're going to look at an example here in order to practice this equation. So it says, consider these two elements that we have. And so from these two elements, it gave us a phase diagram below. And so what we're going to see is the weight percentage of copper here is on our x-axis. And so if we say it's 60% copper, then it's 40% of the other element here. And so we're going to look at what is the equilibrium percentage of beta in an alloy of 30%, and then we have our minority element, and 70% copper, which is the majority element or the host ingredient. And so at 900 degrees Celsius. And so here, in order to determine the weight percentage of substance beta, what we're going to do is, remember from the equation, we're just applying it here. No need to memorize it. It's X and then minus X of alpha. And so, how did I know this? How did I know where to plot X? Well, it said X basically, remember, refers to the composition of your materials. And so here we have our 30% of our minority element and 70% of our host ingredient element. So here is our X. That's the composition amount of each. And so we're at 70% of copper. So this is our X right here. It's basically at 70% of copper. So this point right here refers to my X. And then how much percentage composition of substance alpha? And so what we're going to do is we're going to notice that our X of alpha, what is that referring to here in this case? In our X of beta, basically within this diagram, we're going to see that what you're going to tell is your alpha is going to be your one substance, remember, and your beta is the other substance. So we're going to have to determine which one is which specifically for this composition. But let's keep looking at the diagram because there's one important note that we need to take into account. It's at 900 degrees Celsius. And so right here, this line here, the 900 degrees Celsius, let me draw that so it's better over it. Okay. So here's our 900 degrees Celsius line. And so we got our line right here, and that's great. And what we have to determine from this line is, okay, we know it's the alloy of 30% and then our minority element and 70% copper. And so we were able to plot the point. X basically is our composition, so it runs along this entire line here. So we have our 70% basically of copper. So 70% anywhere along here is at 70%. And it's at 900 degrees here. And so what we're going to notice here is where do the two intersect? And so notice that they intersect right at this point right here, which is great. So now we're going to call that our actual X, because notice that's where the two intersected with each other. So that's going to be where we're going to be working around. And now that we were able to determine that, we have to look at specifically our percentage in order to determine between the two substances. And notice that on our other diagram from the one before, so let me flip over to the screen right before, that it was taken between 2 points here. One when it was in the solid stage and one when it was also in the solid stage. And so here, though, in our example, notice that at our 900 degrees Celsius mark, that the difference between the two, so this is our intersection point, remember, between the two here, for that 70% composition. Notice that the boundaries that the two substances are between is the line right here before it turns into a totally liquid substance at this point, and over in this state where it is in the solid of beta. And so this is going to be the two boundaries we're working between on our phase diagram, just like in the previous example, how it worked between the two boundaries. And so right here, we're going to notice the boundary values. If we bring this down, you're going to see that just bringing it down, that the composition is about 48%. And so that's going to be the composition we're going to use for our alpha substance here. So our alpha is going to be 48% in this equation. And then what about our beta? Well, if you attach a line basically from that 900-degree line, intercepting it with the composition, how much should we have composition of beta? It's about 91%. And then for the total composition that we were working with, it was 30% of our minority element and 70% of the majority element. For your composition, we're going to use the majority element. And so that's how we can determine the weight percentage of substance beta. And so that's when we're working with specifically these binary phase diagrams, how to interpret them. Now that we talked about that, we're going to look into crystallography. And so crystallography, what it refers to is crystal lattices. And so you can think of like the shapes in crystals. The shapes of crystals, so crystal lattices. And so what I like to talk about here is the unit cell. And so the unit cell, if you think about it, it's just one unit. So it's literally just one of these many cubes you sort of see in this little illustration here. So it's the smallest cube you can think of, the smallest one you can get in there. No other cubes fit inside it. It's the tiniest one that you can have and replicate that cube in order to form your crystal lattice. So the crystal lattice just refers to you have a lot of these cubes all attached to one another. So the unit cell is the smallest repeating structure within this crystal lattice. And so there's three common types of forms for these crystal lattices. And what you're going to notice is that there's just the body-centered cubic, which, what do I mean by body-centered cubic? Notice that all the other atoms at the other corners, they're all at the corners, but there's one that's at the center of this cube. And so that's what we mean by bodied centered, is they're all positioned around that center one. It's sort of like the sun is the center of our solar system. That's the body. In this cube, that one atom's at the body. Okay. Then face centered. What is face centered referred to? Notice that basically it's on the face. So if we like to just look at this in 2D real quick, the atoms at the face, basically, of each of those 6 faces on the cube. So at the face, it's at that middle point on the face here. So on the top face right now, this one's at the middle of it. At the back face, at the right face, at the bottom face, and at the front face. And so that's what it means by face-centered cubic unit cell, is at each of the faces. It's at the center. And so you'll notice the one at the center here, because we have the 4 atoms at each of the corners. The one that's in the centered is at the face of the atom. It's the atom at the face of our unit cell, that 2D representation. And so that's why it refers to face-centered cubic unit cell. Okay, so let's look at these calculations. So for crystal forms, if we have a unit cell here, so unit cell, right now we're looking at the simple cubic structure. And so what we're going to notice is how many atoms are within this simple cubic. Well, you got to recognize that these atoms are a sphere. And so you're going to notice that only 1/8 of the atom is actually within this cell here. So 1/8, meaning this sort of corner of that atom, this little corner, the atom, there's only 1/8 of it that is within the actual unit cell. Because if you look up at the lattice structure, you'll see here, look at this one atom right here. And notice that it's shared between 1, 2, 3, 4, 5, 6, 7, and 8. There's 8 different unit cells that it's shared between. So it's split into an eighth. It's equally shared around. So this one right here is 1/8 of it is in each unit cell. And so that's why for our unit cell, there's an eighth from each atom times, and then we have 8 atoms actually in this unit cell. And so what you're going to notice is that in total, there's one entire atom because it's an eighth multiplied by, and we have 1, 2, 3, 4, 5, 6, 7, 8. And so 1/8 of an atom times 8 total atoms is 1 total atom within that unit cell. Now for the body-centered cubic, we actually have 2 atoms. And so we have 1 atom at the dead center. And then we have an eighth of an atom at each of the corners. And so if you do the calculation, it's going to be 1 atom at the center and then an eighth of an atom at each of the 8 corners. You're going to get 2 total atoms can be stored within a body-centered cubic unit cell. And then the face-centered cubic unit cell, you're going to notice that it can store up to 4 atoms inside of it. And so what we're going to see here is that at the face, remember on the face, what we're going to notice, let me try doing this 3D representation might help a little more. And so half of the atom is going to be on this face, where the other half of the atom will be on the other face. Because if you think about the diagram up here, if it's on the face, so if you think about the atom, if it was like on the face here, it's going to be shared between this one, this unit cell, and the one behind it. And so half of the atom is going to be split between those two that it's sharing between. So only half of it will be on one unit cell, and then half will be on the other unit cell next to it. And so that's why we have half an atom on each face times 6, because we have 6 of these faces to our cubes, the front face, the back face, the left face, the right face, the top face, and the bottom face. And then we have an eighth and an atom at each of the 8 corners. And so that makes 4 total atoms stored within this face-centered cubic unit cell. Now that we talked about that, we're going to move on to the atomic packing factor. And this is sort of where you can see a good representation of our unit cell right here. But notice how it enlarges the atoms at each of the corners. And so you can see how only an eighth of the atom is within each of the corners. And so I think this diagram does a good representation of illustrating the unit cell and how there's an eighth of each atom in each unit cell, and then there's times 8 total atoms at each of the corners to make 1 total atom within that unit cell. Okay, so atomic packing factor. Think of this is how many, if you like to think about it, you're trying to pack in your atoms. And so we're trying to determine the atomic packing factor for unit cell. And so it's the number of atoms multiplied by the volume of the atom all over the volume of the unit cell. In the volume of the unit cell is like the actual space that you can store it within. So that makes sense. That's our limit. We can only store within the actual volume of our unit cell. And so the volume of the atom, how much does that atom take up? And so how many atoms can we actually store within there? And then times the number of atoms that we have. So let's look at the atomic packing factor for unit cell. And so within a unit cell, remember, we have 1 atom that we can store within it. And so an atom is a sphere. remember, each atom is a sphere we have. And so if you recall, the equation for the volume of a sphere is 4 pi r cubed all over 3. And so that's just a geometric equation. And then all over the volume of a unit cell. Well, unit cell's a cubed, right? So when you have a cube, each of the sides basically are the same length. And so within this cube here, what we're going to notice is that if the side length is A, and then the height is A, and then the actual depth is A. So remember, the volume is equal to the length times the width times the height. And so the length times the width times the height, if they're all the same, they're all A, then volume is just going to equal A cubed because it's going to be A times A times A. So the volume of the unit cell is going to be A cubed. Okay. So that's why we have that in our denominator. And what we're going to do is we're going to substitute in for A in order to have it cancel out one of our other factors. And so notice that we can rewrite A in terms of R, so it can try and cancel this R here in the volume of the actual atom equation. And so what we're going to see is that our A, which is the side length, isn't that 2 radiuses? So our radius is given here. And so you're going to notice that is going to be 2 radiuses here. So A, if we have 1 radius, which would be length of here, and then 1 more radius. So if we have R plus R, that's going to give us 2R, which is going to be equivalent to 1 side of the unit cell. And so that's why we said 1 side of our unit cell is going to equal 2R. So we're plugging that in for A. So 2R and then cube it. So our atomic packing factor, what we're actually going to get is when you work out the math, it's going to come out to pi over 6, which is equivalent to 0.52 for your atomic packing factor. And now that we talked about that, we're going to go to the coordination number. And so the coordination number is the number of closest touching atoms. So for this atom at the center, you're going to notice that how many other atoms is it touching? And so it touches 1 above, 1 to the left, 1 in the front, 1 in the back here, 1 to the right-hand side, and 1 below. It's connected to 6 other atoms. And so that's what we're going to see. Is the coordination number refers to how many atoms it's actually connected to or touching. And so what we're going to tell is for a unit cell, because that's what we have. We have just our basic unit cell here. It's not body-centered cubic. It's not like face-centered cubic or anything. Right now, we're just working with our simple cubic. You're going to notice it has 6 neighboring atoms. And so just like we counted there. Okay. Now we're going to move over to Miller indices. So Miller indices is basically classifying the planes we're working on in our crystal lattice. So a plane, remember, when you're working on your XY plane, you can think about that. You're used to working in the XY plane here, so that's a 2D plane. And so right now, we're going to now work with the 3D plane. So it's going to be X, Y, and Z. And so the cell dimensions, A, B, and C, are going to refer to the respective X, Y, and Z axes. And so A to X, we're going to have B for Y axis, and then C is going to be for the Z axis here. And so Miller indices are calculated as the reciprocals of the plane intercepts on these axes. And so if a plane does not intercept an axis, so see how this diagram, it is not intercepting. So right now we have our X coming outwards and it's not touching this Y-intercept. We don't see it touching it. It touches the X and the Z, but it doesn't look like it's going to touch this Y-intercept here. It's just going to pass by it, but it touches our X and our Z axes. So the big thing here is it's never going to intercept with the Y axis. So when we write it, you're going to notice that, oh, we wrote a 0 here, but it never intercepted. Remember, in the Miller indices, these are the reciprocals. So 1 over infinity is 0 because it's 1 over a super large number. So it's approximately 0. And so what we're going to see here is the ones. Basically, that is because it actually intercepted at the point. So this was 1, and this was when x equals 1, and this was when z equals 1. So 1 over 1, if you take the reciprocal of that, you just get 1 here. 1 over 1 for this point. So reciprocal would be our 1 over 1. Then reciprocal would be 1 over and then 1. And so that's how we got the x and z Miller indices here. And so what we're going to see is there's a little bit of syntax things that you need to look out for. And so you can't have fractional intercepts. So what we do is notice how here we had a fraction in our Miller indices. We multiply each of the indices by the same constant in order to produce integers. And so right here, we multiply, it looks like the denominator, the least common denominator would be 2. And so we multiply everything by 2 to remove the fraction. So multiply 1/2 by 2, you get 1. Multiply 1 by 2, you get 2. Multiply 0 by 2, you get 0. Okay, then the next one down here is indices are reduced to the smallest integers. So you don't write commas in between the indices. You make sure to reduce them to the smallest integers so you don't have multiples. And overbars are used to designate negative numbers. So we're going to fix this one right here. This is the incorrect one on the left-hand side. And so we're going to try and fix it. So remember how we can't have multiples. We have to have the smallest integers. So everything's divisible by 2 in order to retain it in the whole number format. So I'm going to divide the first index by 2, the second index by 2, and the third index by 2. And now we're going to get rid of this negative sign in front. So in order to get rid of the negative sign, I'm going to use an overbar. And so that's why you see the 1 has a bar above it, is to indicate that it is a negative number. Okay, now we found out what Miller indices were. We're going to get a little bit into ionic bonding. So ionic bonding refers to anions, so negatively charged, and cations, which are positively charged. And so negatives and positives, opposites, right? So they're attracted to each other. And so anions and cations, they sort of attract each other because of their charge. And so they are attracted to each other by the electrostatic force, which we refer to as ionic bonding. And so an anion, you can think of it as it has one more electron, so it has a net negative charge. And so in the diagram here, notice that the anion has more electrons than the cation. The anion has 5 electrons, whereas the cation has 3 electrons. And so because the anion has more electrons, it is negatively charged, because what you're going to notice is in between, in order to not have a specific charge, you're going to have 4 electrons. So silicon is often where we like to be at because it has 4 electrons on its outer, so it's not net positive or net negative. And so that's why cations and anions have a net charge, because they have 1 less than the 4 total electrons. Cations, they have 3, so it's positive because there's 1 less negative charge, so it's more positively charged, where anions have 1 more electron than the normal balance of 4, so it's more net negatively charged. And so what we're going to notice is that 1 or more electrons can be transferred from the valence shell of one atom to the valence shell of another. And so what you're going to notice is that an anion oftentimes doesn't like to have this 5. It wants to be back to that 4 valence state of electrons. And so a cation, it only has 3. So it has 1 empty room, you can think of it. So an anion will try basically transferring its electron over to the valence band of the cation, because the cations are positively charged, so it will take a negative charge. It's like, oh, gimme, gimme, gimme. And so it's going to fill a vacancy within the cation to make 4 electrons in its valence band, whereas the anion is going to have 5 of these electrons within it. So now that you've seen these 2 different types of models for anions and cations and how they each have net charges, a little mnemonic that I like to have is that cats have pause, right? So cations are positive, positive, if you get it. So I thought that was cute to remember it. That's a good way to keep those 2 straight because they often get confused. So here we're going to look at common bonding models. And so for covalent bonding, we just looked at ionic bonding. Covalent bonding has several common gases in their free states called, they basically exist as diatomic molecules. And so what we're going to see is H2O, you can think about that. In our H2O water, isn't hydrogen sort of like in that diatomic state? And then carbon dioxide, CO2, you'll notice that, oh, there's 2 oxygens, but here we have 2 hydrogens. And so what if we just have 2 hydrogens? We don't have this oxygen. It's just H2, or we just have 2 oxygens, just O2. So here's a representation where we have just O2. We have 2 of those oxygen molecules. And so this is known as diatomic when we have 2 of them. Just like when we said carbon dioxide, there's 2 oxygen. So that's known as covalent bonding because they share electrons. Notice how each of the oxygens have 1, 2, 3, 4, 5, 6 electrons, but in between, because on the periodic table, they like to be at that 8 filled valence electrons in their outer shell. So they share these electrons in order to get to that state of 8 total in their valence bond. So they'll count it as 1, 2, 3, 4, 5, 6, 7, 8. And the other oxygen molecule, when counting its electrons, 1, 2, 3, 4, 5, 6, 7, 8. So each of them have 8, so they're both at their totally full valence electron state. And so because they share those 2 electrons with each other, they're able to get to that happy state of 8 valence electrons. So now that we've seen the covalent bonding, we're going to look at the metallic bonding, which is a sea of free floating valence electrons that are attracted to metal cations. And so from this diagram, I think this does a better job. So notice that we have these floating valence electrons. And so here we have these electrons right here. We see, and they're like floating through. Woohoo! And so what we're going to notice is that they're attracted to the metal cations. And so our metal cations here, remember, cats have pause, so they're positive. You can think of cations. So here we have a cation. It's positively charged. So these electrons flowing through are going to be attracted to that positively charged cation. And so it's a sea of electrons. So like a sea, you can think like them going over, like waves, just like a wave while surfing. It's like moving over. It's a sea of electrons. They're just like all moving throughout. And so they're going to be attracted to those cations. And so that's called metallic bonding. Okay. Now we're going to look at amorphous materials. So there's 3 types to materials you can classify them as, is crystalline, polycrystalline, and amorphous. And so what we're going to notice is crystalline. Think of it as perfect structure. Everything's like crystal. It's perfect in order. Polycrystalline, there's some structure, but it's not totally uniform. So notice that it looks like there's structure here that these guys are together. These guys are together down here. And these guys are together. And so there's 3 different structures happening within here. So there's order, but it's not all one order as compared to the crystalline where they are all in one order. Amorphous means that there's just no crystalline structure here. It's basically, it's all over the place. Like there's no order, each individual one here. So that's what we see between the 3 classifications is you look at the order. Is it all one order? It's crystalline. Is there some order? Then it's polycrystalline. Is there no order? Then it's amorphous. And so glass is an amorphous material, just so you know. Now, conductors versus insulators. So conductors have high electrical conductivity. And so in electrical engineering, we work with a lot of conductors. And so they pass through a lot of current. And so they have little resistance. They're willing to let current just pass through. So copper is a really good example. Aluminum and silver are both really good conductors at having electricity flow. Now, insulators have low conductivity, so low current can pass through, not much. They have higher resistance. They're like, stop sign, slow down. That's what they're trying to do. So wood, plastic, and ceramics are insulators. They slow down the flow of electrons. And so that's what we're going to be talking about is within conductors, you're going to see like these electrons are moving around. It seems like they're moving freely. Whereas in the insulator down here, doesn't look like they're moving as much. There's not really action happening here. So insulators, it slows it down. So we're going to notice that conductors, we like them because they allow electrons to travel through. So if we have an electron here, it can easily travel. So current can flow because current is the amount of electrons you have flowing through a specific area where we're going to see with insulators, what happens is insulators, what they do is they impede the flow. They make it harder. So you can think of within the pipe here, they sort of make it a little bit harder. So like now this electron has to like go through the small thing. They add resistance. They sort of like block the flow of the electrons. They make it more difficult for them to flow through the material. Now, semiconductors. Semiconductors fall between the 2 of conductors and insulators. And so semiconductors, a material which has electrical conductivity falling between that of a conductor and that of an insulator. And so we like them because you can, depending on the temperature, it acts more as a conductor or it can act more as an insulator. So one common example of a semiconductor is silicon. You see that everywhere you go. And so what we're going to notice from this curve is that as you increase the temperature, so as temperature increases as you go, right, the resistivity is going to drop. And so as you increase the temperature, it becomes more conductive. But at higher temperatures, it's more like an insulator because it's more resistive. So here at higher temperatures, it's more like an insulator. But at lower temperatures, it's more like an insulator. But at higher temperatures here, you're going to notice it's more like a conductor because it has less resistivity. So those electrons can easily flow through that material. There's not going to be an impedance or obstacle in the way. Okay, now that we talked about that, you're going to see silicon widely used as a semiconductor. Germanium is also used. Those are the most common types that you're going to run into. Now, dielectric materials. It's basically an electrical insulating material used where an electric field must be maintained. So oftentimes when I think of dielectrics, I think capacitors. It automatically comes to mind. So when you have a capacitor, we're going to dive a little into this within this chapter, but it just has a separation of charge across it. And so we notice this separation of charge here, and an electric field is going to build up basically from this negative going over to, from the positive charge to the negative charge. That's going to be the direction of our electric field, is it goes from the positive charge here to the negative charge. And so I indicate the electric field line with this E with like a little hat on top of it. So there's an electric field. It's basically from the positive charges over to the negative charges. That's what an electric field is. And so what's going to happen is we want to maintain this electric field because you're going to realize that a capacitor is a circuit component that stores energy. So it stores energy within its electric field. And so we want to maintain this electric field here. So we don't want these positively charged ions coming over to this negatively charged region. We want to maintain this electric field. So we use a dielectric in between. So it makes it hard. So this dielectric material in between won't allow these positive charges to go towards these negative charges. And so that's what our dielectric material is going to be used as, is it impedes the flow so that the electric field will be maintained and that there will remain a separation of charge between these two capacitor plates. Now that we talked about that, we're going to get into the properties of materials. And so there's different types of properties. There's physical properties. So this can be like the density, how dense something is. What's the melting point? When is it going to turn into a liquid from a solid state? What's the specific heat? And now we're going to get a little into the electrical side. What's the conductivity? How conductive is that material? What's the permittivity, or what's the resistance? How much does it impede the flow of electrons? Magnetic, so this would relate to magnetic field lines. Thermal refers to, of course, like heat. So we're going to see thermal conductivity, diffusion and fusion. And then we're going to see mechanical, which deals a lot with stress and strain curves and applying forces. Then chemical is going to deal more with the oxidization, corrosion, and flammability. And so density, how I like to think of it, is how dense something is how tightly packaged it is. And so we're going to notice a substance that's more dense, it's going to have a lot more stored within it. So here you can see there's a lot more happy faces within this square. So it's more dense. There's more stored within it. Whereas on the left, there's less happy faces. So it's less dense. And so solids tend to be more dense because it's all packed together. Where gases, it's more spread out. They can move throughout the air. So we're going to see that gases are less dense and liquids are in between that of solids and gases. So density, just like we talked about the equation, so that makes sense. Density is indicated by the P here, but it's equal to the mass all over the volume. So how much volume does that mass have within that specific space? So it's basically the amount of mass that you have within the space. And so we can see that there's more mass here. We have more of these happy faces. So it's going to be heavier. Whereas this gas, it's going to be lighter. It's less dense. There's less happy faces within this square. And so that's what the equation's trying to tell us, is how much mass do we have for the volume that we are working in. And so specific volume, you're going to notice it's the volume occupied by one mass. So it's the volume occupied by one mass. So divide by one mass here. And so that's what specific volume refers to. And you're going to see specific weight, specific gravity. So specific, it just refers to dividing by a certain factor. So determine the specific volume from a 1 in a meter cubed volume of gas with a mass of 1.2 kilograms. So specific volume, remember, you take the volume and you divide it by the mass, and that's how we got our result here. And so let the units do their magic. Volumes in meters cubed divided by mass, which is measured in kilograms in the metric system. And so you get meters cubed per kilogram. Specific weight, you're going to notice, is known as the unit weight. And so it's the weight of substance per unit volume. So just like with specific volume, where we divided by the mass just to get basically the volume occupied by one mass, weight is known as getting the weight per 1 unit volume. And so what we're going to see here is you take the weight and you divide it by 1 unit volume. And so here, weight, if you remember from physics, it's just the mass times the gravitational constant. And so divided by 1 unit of volume. So that's what we're going to have here when we solve for it. Basically, we're going to see determine the specific weight given the density. So density, remember, is symbolized by P. And so specific weight, it can also be density times the gravitational constant. And so plugging those in, you're going to notice the meters cubed is going to cancel one of them with the meters here. So you're going to get meter squared in your denominator. And in the numerator, you have kilograms. And then in your denominator, it's meter squared times second squared. And so that's how you solve for specific weight. It's dividing by 1 unit of volume, but you can see that you can rewrite this in order to get your density, because remember, right, isn't density mass divided by volume? And so that's how you can solve the equation. You can put it in terms of density. And so if you're given the density, you can determine the specific weight from that information. Specific gravity is a dimensionless ratio of a substance's density to a standard reference density. So here's the substance density. Divided by the denominator here is the a reference density. So a lot of times this reference density is referred to the density of pure water, which is 1,000 kilograms per meter cubed. And so what we're going to see here is within our specific gravity, for example, they told us that a liquid substance has a density of 740 kilograms per meter cubed. So calculate the specific gravity. To calculate the specific gravity, you're going to notice that we take the density, which we were given 740 kilograms per meter cubed, and divide that by reference density, which is usually pure water, which is 1,000 kilograms per meter cubed. Notice that the units are going to cancel, so you're just left with a unitless number. Now, viscosity. What does viscosity refer to? It's basically a measure of a fluid's resistance to flow when acted upon by an external force like gravity. And so let's look at the examples here. So water, when you pour it down, it basically, when it hits something, it just goes all over the place. And so you can think if you just drop water on the floor, it's just going to go everywhere. And so it has a low viscosity. It doesn't have much that makes it resistant to flow. It will just go everywhere. If you drop a bucket, all the water goes all over the place. But honey, it's a little slower. It's a little more resistant. It like slowly drops, you'll notice here. It doesn't drop fast, even though it's a liquid substance. So it's a higher viscosity. It takes it longer in order to flow. So it's higher resistance. It doesn't flow as easy. It sort of resists the impediment of the movement. So you're going to notice that substances with lower viscosities, it goes all over the place, where higher viscosity is very slow moving, that substance. Okay, now kinematic viscosity is the ratio of absolute viscosity to mass density. And so we're going to look at an example of this. But absolute viscosity divided by mass density here, we're going to notice that within our units, basically the viscosity referring to that flow of that liquid, basically our absolute viscosity divided by our density, so how dense it is, that's going to determine our kinematic. And so you can think of kinetic energy like the actual movement. So it's going to determine the actual movement of that substance. So how fast that liquid is able to move, or like that type of substance, by taking the absolute viscosity and dividing it by the density. So how dense it is. Okay, so water flows at 3 meters per second through a pipe. The viscosity of water is 769, and then micro newtons times seconds all over meter squared. And the density of water is 995 kilograms per meter cube. Calculate the kinematic viscosity of water. So here, we're going to notice the kinematic viscosity using our equation, our absolute viscosity in the numerator here. So here they gave us the viscosity of water. So I'm just plugging that in right here for my numerator. And in my denominator, we were given the actual density. And so solving for that, we're able to get our result. Notice it didn't matter the actual flow rate here. We were interested in the absolute viscosity divided by the actual density of that substance. Now we're going to talk about pressure. So pressure is force per unit area. And so this diagram does a really good job. You can see all the force. You can think of this sort of like maybe gravity, like, pulling down. And so it's pushing this substance downwards to fall to the ground. So the amount of these force lines that are going through this area that we have here, that's referred to as the pressure. If you have more force per unit area, so then we have like a bunch of these lines in here going through, that is a higher pressure. But say we only have a few, then it's a lower pressure. There's less force per unit area. And so force is in units of newtons, and then area is in units of meters squared. And so what we're going to notice is that pressure is in units of newtons per meter squared or pascals. So Pascal is equal to a Newton per meter squared. And so in the US system, though, they say pounds per force over inches squared, but we're going to be working a lot of times with the metric system. Okay, now that we talked about that, we're going to look at fluid pressure. So fluid pressure refers to two pressure references, zero pressure and atmospheric pressure. And so what we're going to see here is within the diagram, pressures are measured with respect to true zero. So when we talk about true zero, that's absolute zero here. So notice how a lot of these pressures are measured from this point. So this one's measured from here, this one's measured from here, this one's measured from here. So they're all from this like absolute mark right here, those three different pressures. So they're measured with respect to the true zero. So at this base 0 point. So those are known as the absolute pressures. So our absolute and our absolute pressures when they're measured from that base 0. Now pressures measured with respect to atmospheric pressure are known as gauge pressures. So atmospheric pressure, notice that this local atmospheric pressure right here, this one, if you measure with respect to the line right here, that is known as a gauge pressure. And so notice how this one measures with respect to that line. So it's a gauge pressure. And so to distinguish, the word gauge or absolute can be added for measurements. And so a lot of times pressure is assumed to be absolute. So, when we're talking about absolute pressure, it's with reference to absolute zero as the base. And so now that we talked about that, let's look at a visual to have a better understanding. And so what we're going to see here is absolute pressure is the measurement of pressure basically relative to absolute zero pressure. So it's the entire system's pressure. And so what we're going to see here is with reference to absolute zero, let's look at this example. So within the atmospheric pressure, which is due to the Earth's atmosphere, we're going to see that higher altitudes have lower pressure because there's less air above you. And so what do I mean by that? Is basically when you're at higher altitudes here, there's less air, meaning that, remember our Earth here? If you're at the point here, there's only this much air between you. But if you're down here in like the center, there's more air between this gap, the outer rim, and you. So within this point, there is less air pressure, but here there's more air pressure because there's more pressure for it to touch on you as the observer down here. So what we're going to talk about a lot with atmospheric pressure is the air pressure due to the Earth's atmosphere, but the measurement relative to absolute zero, this is the entire system pressure. So notice from our diagram before that absolute pressure, basically versus the atmospheric, absolute is the entire pressure of the system. Notice it's the entire pressure right here, where atmospheric is only a part of that total. And so absolute takes the total sum of the pressure. And so now gauge pressure, it's pressure relative to the atmospheric pressure. And so it's the difference between the absolute and the atmospheric. So notice in the fluid pressure diagram, when we had our absolute here, and then we had our atmospheric pressure, the difference between these two was the gauge pressure right here. And so that's what gauge pressure is referring to. It's the difference between the two. And so that's why in the equation, when they talk about absolute pressure, it's the total system pressure. So it includes the atmospheric and the gauge pressure. But if you want to solve basically, another way you can do it is you take the atmospheric and you minus the vacuum gauge pressure reading, but we won't get into that one. What I want you guys to know is the total system pressure is the summation of the atmospheric and the gauge pressure. And so standard atmospheric pressure is equal to 101.3, and this is kilopascals. And so that's what we're going to see. And so right now we're going to work with an example and we're just going to use the equations, but now you understand where this first one came from. And so if they ever referred to basically a vacuum gauge pressure reading, then you actually subtract it, just a heads up. But if they just refer to gauge, then you add it. So it says a vessel is initially connected to a reservoir open to the atmosphere. The connecting valve is then closed and a vacuum of 65.5 kilopascals is applied to the vessel. So it talked about a vacuum, so I'm going to be using the second equation here. And it says assume standard atmospheric pressure, calculate the absolute pressure in the vessel. So standard atmospheric pressure was 101.3 kilopascals we talked about. And so minusing the pressure in vacuum, the vacuum gauge pressure reading, we're going to get 35.8 kilopascals for absolute pressure. Okay, now that we talked about pressure, we're going to get into the specific gas constant. So this is how much mechanical work you obtain by heating a unit of mass of gas through unit temperature rise at a constant pressure. So what we're going to see here is our specific gas constant is going to equal our universal gas constant all over our molar weight. And so our specific gas constant here, which is the R on the left-hand side, what it represents is it's the amount of work. So we're dealing with work here, and work is energy, obtained by heating the unit mass of a gas And so through a unit temperature rise at a constant pressure. And so 1 unit of temperature rise at a constant pressure to heat 1 unit mass of gas. And so that's what a specific gas constant refers to, is how much energy is produced by heating 1 unit of mass by 1 unit temperature at a constant pressure. And so notice that here, within our universal gas constant, this one's constant. And so that's what we're going to be working a lot when we have to calculate our specific gas constant. So it says air is an ideal gas with a molecular weight of 28.967 kilograms per kilomoles. Calculate the specific gas constant. So here, if we need to solve for a specific gas constant, it's going to be, and then remember, this is just our universal gas constant, 8,314 joules per kilomole times Kelvin. And so the denominator here is going to be the molecular weight. And so what you're going to see is when you calculate that, you get the specific gas constant to be 287.016 joules per kilogram times Kelvin. Now that we talked about that, got really heavy into our gases, we're going to just talk about a little more, and then we're going to get into the electrical side soon. And so elastic collisions, what these refer to is you're going to see these that there's no loss of energy. And so it's ideal. So look at these two masses here. There's going to be a collision. And so they're going to collide with one another. And so when they collide with one another, they just bounce off. They don't lose any energy. So they just bounce off. But when we have an inelastic collision, the energy isn't preserved. Some of it's lost. And so here, notice that this ball is going to hit this one over here. This one isn't moving. And so it's going to come in contact, and then it's going to cause this ball to start up and start moving. But the kinetic energy is not going to be conserved. It's not going to go at the same rate. It's going to have a little bit of energy loss. And so notice with the elastic, it just bounced off, and then there was no loss of energy. They were both moving, and then they bounced off, so they kept moving. But here, one wasn't moving. So you have a little bit of energy. Kinetic energy isn't conserved because now you have two objects in movement, where before you only had one. So there is a change. One went from just potential energy because it was just sitting there and now it got kinetic energy. So it lost some of its potential. Now it got more kinetic energy. And so that's what we're going to see within our examples. But here, both had kinetic energy going in, and they had kinetic energy going out. So right before we get into our electrical side, we're going to just cover the ideal gas law. And so an ideal gas is in which all the collisions between atoms or molecules are perfectly elastic. There's no energy being lost within your system. And so it follows the behavior of this equation, where it refers to the pressure times the specific volume is equal to your specific gas constant times the temperature. And so notice that here, you can just write it in terms of the volume. Remember, your specific volume can be written as volume divided by mass. And so that's what we just did here, but we move mass over to the other side. You can also basically represent it here if you have two objects per se. So we have pressure 1 and specific volume 1 over temperature 1. And we have pressure 2, specific volume 2 over temperature 2. What we did here is this was just, if we have two different objects here, writing them equal to one another, what would happen within that system to make sure things are conserved. It's elastic. What's on the left-hand side is going to equal what's on the right-hand side. And so remember how you can always write the final minus the initial. So that would be like V2 minus V1. So here we're just talking about two different instances of V1 and V2. The left and right hand side are going to be equal. So this could be two separate substances that are coming in contact. It's going to be equal afterwards. So each one. So we're going to look at an example where we deal with 0.5 cubic meters of superheated steam, has a pressure of 400 kilopascals and a temperature of 300 degrees Celsius. So we need to calculate the mass of the steam. And so if we're thinking about mass, we're probably thinking about our ideal gas law. This is great to get the mass from. Just rewrite it. So we can rewrite it this way, which is great. And so we know the pressure, we know the volume, and we know the temperature. And ours, we don't know though. So we have to calculate our specific gas constant. And so remember, the specific gas constant, if you remember the universal gas constant, here divided by the molecular weight, which here we have 18 kilograms per kilomole, and we're able to get our result for the specific gas constant and plug that in order to solve for the mass. Okay, now we're going to talk about capacitance. So capacitors, this is a big thing. It stores charge on its plate. So on one plate, it will have positive charge. And then on the other plate, it's going to have negative charge. So you can either have positive charges or negative charges. And so it's going to store the difference between those two charges, and an electric field will be created from the positive to the negative charges. So an electric field is going to exist in between those positive and negative charges, pointing from the positive to the negative charges. So a capacitor has two conducting surfaces separated by an insulator, also known as a dielectric material, between those two plates. And so a parallel plate capacitor is a simple type of capacitor with two parallel plates. And so if the plates are connected across a voltage potential. So we're going to look down here at this diagram. So there's a voltage source, which we see our battery, and the positive terminal is going to be hooked to this side, and the negative terminal is going to be hooked to this side. So opposite polarity is going to build up on each of the plates. We're going to build up positive charge on this side and more negative charge on this side. And so that's going to create that electric field from the positive end to the negative end. And so that's our electric field between those two capacitor plates. And so the amount of charge that is on those plates, you can actually calculate how much charge, so how much positive charge you have or how much negative charge. And it's going to be equal to the capacitance times the amount of voltage you have. And so we're going to be able to calculate the charge is proportional to how much voltage you actually apply. If you apply more voltage here, so if you actually apply 50 volts, you're going to get a lot more charge between these two plates. And so that's what you're going to be made aware of, is if you increase that voltage, you're going to get more charge between those two plates, creating a stronger electric field strength. And now we're going to the next one, which is the capacitance. This one's just part 2, continuation. So capacitance is measured in units of farads and depends on the capacitor construction. So a capacitor has the ability to store charge between its two plates, as we saw before. And so more capacitance, the greater the charge stored, because you can either increase the capacitance or increase the voltage to get more charge. And so here, what we're going to see with the equation is the amount of capacitance is going to equal. And so if we can increase our capacitance, we'll be able to store more charge. And so here, you can increase the area, you can decrease the separation between the two plates. So that's what D refers to, is the separation. Here, separation D is the distance between the two plates. If you decrease the separation, you're going to get more capacitance. Or if you increase the area of the plate, so if you increase this plate area here, so you get a larger plate, you're going to get more capacitance because more charge can then build up on those plates. You say if you have, now there's more room for the charge to build up between these two plates here because there's more spaces for charges to accumulate on. So those are just ways to increase your capacitance of your device. And E, here, it looks like an E here. It's actually an epsilon, and it refers to the permittivity. And so what you're going to notice is, remember, capacitance is in terms of farads, areas in terms of meters squared, distance in terms of meters. And so permittivities in units of farads per meter, if you just do the unit cancellation, you'll get that as your result. So the capacitance of two parallel plates of equal area A are separated by distance D. That's how you're able to calculate how much capacitance is on those you can store up. So permittivity is the ability of material to store energy in the presence of an electric field. And so remember how basically in electric field, capacitors store their energy by that difference in charge, which creates that electric field. So that energy is actually created by that electric field because in order for an electric field to exist, there must be separation of charge. And so if there's a separation of charge, there's energy because there's potential difference between the two sides. And so that's going to create basically your energy stored in that electric field because there has to be a potential difference between the two sides in order to have that electric field created, and that creates energy, that potential difference, and so it's stored in the electric field. Epsilon refers to the permittivity of the medium separating the two plates. So what we're going to see if we have a higher dielectric constant, so the material we use in between the two plates, if it has a higher dielectric constant, we'll get more capacitance because that means we'll have a higher permittivity. So higher capacitance, so more charge can be stored. And so notice that the permittivity of vacuum here, it's with reference to, which is 8.85 times 10 to the negative 12 farads per meter. And so now we have two parallel plates separated by 0.2 centimeters insulator with a dielectric constant of 2.6. So in order to calculate the capacitance here, we're first going to calculate what's the actual permittivity. So remember, epsilon naught, that's just the permittivity of vacuum. That's a constant, and then it's going to be multiplied by the actual dielectric constant in order to produce the permittivity. And so capacitance is going to be that permittivity, which we just solved for, times the area of those plates all over the distance between the two plates. And so in order for this calculation to work, we have to convert from centimeters to meters so that the units cancel properly in order to get it in terms of farads for our end result. So now we're going to talk about resistance and why it's so important within electrical engineering. So resistance basically is measured in ohms. And so it's the property of a circuit or circuit element to oppose the flow of electrons. And so what we're going to see here is, let's look at a water analogy. In this water, it's going to have more resistance if the pipe is made narrower. So see here, there's more resistance because the pipe's made narrower. There's less resistance here because the pipe is the same width all throughout, so more water can flow. Where here, there's going to be less water flow in this middle point, so less at the output because less can flow through. So just like this, when we have an electric circuit, so we have electrons flowing instead of the water. And so resistance basically makes it difficult for those electrons to flow. It can, you can think of it as either making the pipe narrower, so maybe it's a smaller width of the pipe, so there's less electrons that can flow through, or you can think of it as causing an impediment along the pipes or like a blockage point, so only a few can go through. That's basically resistance. It's just making it harder for those electrons, those subatomic particles, to flow through. So a short circuit, that refers to right here, it's a short, it's just connected, it's just a metal rod. it has zero resistance. So infinite current can flow through, zero resistance. So as much can flow through as it wants. There's no resistance. Where open circuits have infinite resistance. There's no current flow. So notice here, it's open between these two terminals. There's no metal rod connecting these two. It's just an open gap. And so that would be infinite resistance. So you can think of it like a resistor with infinite resistance. So here, like a resistor in between, and this resistance is going to equal infinity because no current's going to pass through. It's going to be impossible for those electrons to flow. Whereas with the short, there's going to be infinite current flow. Those electrons can flow through. They have a path to flow through. Here, they don't have a path. They get stopped right here. Can't pass through. So now that we talked about that, resistance depends on the resistivity. So the resistivity of the material, the length of the wire, so how long that wire is. Longer wires have more resistance because those electrons keep hitting, like the sides of the wires. And so those collisions make them slow down. And then the cross-sectional area. So how much cross-sectional area is there for an electron to flow through? Is it wide or is it narrow? If it's more narrow, there's less electrons that can flow through. If it's wider, that means more electrons can flow through that cross-sectional area. And so what we're going to notice is resistance is dependent upon the resistivity of the material, the length of the material, so how long that wire is, and then the cross-sectional area. So how large is it for those electrons to traverse through that wire? Is it a big wire or is it a small one? And so resistivity is dependent upon temperature. So at higher temperatures, it's more resistive for a conductor. So notice that conductors at higher temperatures, it becomes more resistive, just like the graph shows. But for semiconductors, remember semiconductors have the properties in between conductors and insulators. The higher temperatures, it becomes less resistive. So notice as you increase the temperature, semiconductors become more conductive, whereas conductors become more resistive. So it's sort of interesting. It's sort of like the opposite relationship. The conductors become more resistive at higher temperatures, whereas semiconductors become less resistive at higher temperatures. And so we're going to notice with resistance here, basically our resistance, it's going to be equal to here. And then what we're going to see in this equation, this thermal coefficient of resistance, here we have our temperature and then what our actual temperature. So if we have like a change in temperature or anything, that's what this equation is taking into account, like our original versus what happened. So if we had a change in our system. So we're going to look at an example here, which will better define it for us. It says, calculate the resistance of a 200-meter copper wire with a diameter of 1 centimeter at 0 degrees Celsius. So here the resistance, what we're going to notice is it's equal to the resistivity, which, did we get supplied that? I don't see that right now, but do we know the resistivity of copper? That's a big thing. And so what we're going to see is if you look this up online, the resistivity of copper is 1.55 times 10⁻⁸ ohm per meter, times meter. And so the length of the wire, they did tell us the length, 200 meters. And so we got 200 meters here. And then all over pi, so pi here, times, and then this is the area. And so if you like to think about it, our area, remember how basically if we have a copper wire with diameter of 1 centimeter, so remember how we have pi r squared, because this is a copper wire. And so the area of just a cross-section area, like if you have the entire wire, it's like a cylinder. If you take the cross-sectional area, so just one slice, and then the radius here is, it looks like a circle, right? That cross-sectional area. So area of a circle is pi r squared, right? So they told us the diameter, which the diameter is the full length across here. And so the diameter divided by 2 gives you your radius. And so that's what we did here, is we took the diameter, divided by 2, and then we just did a conversion factor from centimeters to meters to get it all in the same units. So we solved for resistance to get it 0.039 ohms. Okay, now that we talked about that, we're going to look at magnetic fields. So magnetic fields, which are indicated with a B for magnetic fields. Notice that I put it in bold, meaning that it's a vector quantity. It has size and direction. And you'll see it goes in direction from the North Pole to the South Pole. And it has a specific size. So how large is this magnetic field? So we quantize it. We give it an actual numeric value of the strength. So the magnetic field can exist only when we have two opposite equal poles. So by opposite, we have a north pole and a south pole. And so notice the magnetic field lines run from the north to the south pole, whereas an electric field can be produced by just a single charge product, a point charge. And so here we see the point charge. If we have positive point charge, the electric field lines are radiating away from it. Whereas when we have the negative point charge, the electric field lines are pointing inwards to it. And so that's what we notice is electric fields, there can just be point charges, but there's no such thing as a magnetic monopole. There's always two poles are required, where you can just have a single point charge. So magnetic fields, there has to exist two poles, a north and a south pole, where electric fields, there can just be one point charge. So there can just be a positive point charge or a negative point charge. They don't have to come in pairs. And so notice that the electric field lines run from our positive charges over to our negative point charges. And so now that we talked about that, magnetic fields, just like we talked about, it's a combination of a north and south pole that have a fixed distance between them. And that's known as a magnetic dipole. So remember, within your bar magnet, there's a fixed distance between the north and the south pole. And so the combination of a positive and negative charge, which a fixed distance between them. So here we have our positive and here we have our negative. The distance between them, that's known as an electric dipole. So a magnetic dipole, you have a positive, you have a north and south pole. Electric dipole, you have a positive and negative charge. So dipole, meaning two ends of the magnet, two charges. Magnetic dipole moment is going to be the pole strength times the distance between the poles. And so that's your magnetic dipole moment. And so it is dependent upon your pole strength and the distance between those two poles. Whereas your torque on a magnetic dipole, your torque is equal to your magnetic dipole moment cross multiplied with your magnetic flux density. And so what we're going to see here is that the torque on a magnetic dipole, so torque refers to like your twisting force. So like if you're twisting, so the torque, so the twisting, like if you rotate something like a wrench, if you're trying to screw something, you have torque. You're moving the wrench, you're moving it. It's going to be equal to the cross product of the magnetic dipole moment with the magnetic flux density. And so notice our magnetic flux density is going to be in units of Tesla and refers to the magnetic flux density we'll see in a diagram basically refers to the number of field lines passing through an area. And so the magnetic flux density is the amount of lines we have going through a specific area. And so we see these two lines are going through this cross-sectional area A. So that's what the magnetic flux density refers to, how many lines we have going through a specific area. Okay, so magnetic field strength, separate from magnetic flux density in B here, magnetic field strength is the flux density divided by the material's permeability. It depends upon, of course, just stated before, the material's permeability. And so it's given in units of amps per meter. So for air, the permeability is going to be 4 pi times 10 negative 7th. And then here we have henries divided by meters. And so you're going to notice henries a lot of times are used with inductors. And so we'll get into that a little bit later. But right now we're going to calculate the magnetic field strength. And so we have a magnetic field in air has a magnetic flux density. And so how many of those magnetic field lines are passing through a cross-sectional area of 1 times 10 to negative 8 Teslas. So we need to calculate the strength of the magnetic field in vacuum. Notice how it says in vacuum here. Remember, for air, we know the permeability, 4 pi times 10 negative 7th Henry per meter. The magnetic field here is 1 times 10 negative 8 Tesla. And so we're able to calculate the actual magnetic field strength here. And then we have the specific heat capacity. It's the specific heat capacity, which is given here. It's the amount of heat energy, Q, which refers to the heat energy, required to change the temperature of 1 unit mass by 1 degree. And so notice here we have a change in temperature. Here we have our mass. And here we have our specific heat capacity and our total heat required. So what's going to happen is the total heat required we need, and here we have our mass. So our mass is here, and the total amount of heat required. So how much heat do we have to supply? And then for that change in temperature. And so if the change in temperature is it going to change 1 degree, then we can calculate our specific heat capacity from that information. And so a lot of times they refer to the molar heat capacity, which is usually indicated by capital C, is the heat energy required to change the temperature of 1 mole. So mole's just a number. You can think about it just like a dozen eggs, a gallon of milk. That's just a number, a gallon of milk, or a dozen eggs, 12 eggs. So a mole is Avogadro's number. So it's 6.022 times 10 to the 23. And so it's just a bunch of atoms. If you look at it here, it's 6.022 times 1023. That's a ton of atoms. Is a million's only 10 to the power 6. This is 10 to the power 23. So that's a bunch in here. So Avogadro's number is just literally representing a ton of atoms. That's what you need to know. And so now that we saw that with specific heat capacity, this equation's used a lot of times. It's called the MCAT equation. You can see why it's called MCAT, M, C, and then delta T. And so people like to refer to it as the MCAT equation. Thermal resistance. Remember how we talked about electrical resistance? How it wanted to impede the flow of the electrons we had here. It wanted to make it harder. Well, thermal resistance resists the flow of heat. And so what we're going to see is thermal resistance is dependent upon the length, the path length, divided by the thermal conductivity, and it's also dependent upon the area. And so looking at an example, concrete has a thermal conductivity, and it gives us those specifics. Calculate the thermal resistance of a 20 centimeter thick concrete wall with an exposed face area of 1 meter squared. And so calculating this thermal resistance, plugging in what we know here, we're going to get as a result 0.143 for our thermal resistance. And so it's just going to be how much it resists that heat. So that's what thermal conductivity implies. Now we're going to get into stress and strain, which is very important in terms of materials. So when we're talking about materials, a strong material has high strength, whereas a weak material has low strength. A tough material can take a lot before breaking, so it can yield a lot, where a brittle material will not. It will break pretty easily. A hard material has a high modulus of elasticity, where a soft material doesn't. And so we're going to look at how strength is going to be depicted in this graph. And so what we're going to do here is you're going to see in the stress versus strain curve, what this is going to be, stress here is indicated by sigma and strain is indicated by epsilon. And so our stress versus strain curve, you're going to notice here, engineering stress is the force per unit area. And so how much force we're having per unit area, whereas strain is the elongation of test specimen as a percentage or fraction of the original length. And so this is how much the length of the specimen over the initial length. So if we're changing the length over what our initial length was, so how much we can like strain, like, like pulling it, if we're changing the length compared to what it originally was, we're changing it now. So we're like, and that's what strain refers to, like you're straining it, you're pulling it, where stress is like we're putting more stress on it, more force per area. So we're applying more and more force on top. So stress refers to more force you're putting on it, where strain refers to like you're pulling it out more, you're sort of straining it out. And so notice first when you start straining it out, you're gonna get more elastic. You're gonna be pulling it. It's sort of like elastic, like a spring, you're like pulling it. And so what's gonna happen is it first follows Hooke's law. It looks sort of proportional in the beginning, and then it's gonna plateau. It's gonna get to its elastic limit, and then it's gonna go to the breaking stress, and then it's gonna fracture and bust. And so what's gonna happen here is, notice with the stress and strain curves, you can start applying strain, pulling it, but as you keep applying more and more stress, it's finally gonna just and break in between. So that's what this curve is trying to tell us, is that basically based on the amount of strain and the amount of stress, you're going to get to a point where it's then going to just fracture and break. And so we'll look at an example where we have a 200 millimeter gauge length is marked on an aluminum rod. The rod strain, so the gauge marks are 215 meters apart. Calculate the amount of strain we have. So we had originally 200 millimeters. And so we strained it. So we pulled it out. So it went to 215. So the final minus the initial, because remember it's delta, it's the change in. So the final minus the initial value. So final minus initial value all over the initial value is going to be equal to, and then that's the amount of strain that we have left. And so Young's modulus, it refers to the proportional, the line we have in the beginning. Notice how in the beginning, it follows a linear relationship here. That's Young's modulus, how it refers to that like linear region, where within that line, the slope, your y is the amount of stress, which is indicated by sigma, and your x is the amount of strain, which is indicated by epsilon. So your stress over your strain, and so that's, remember, your stress is the amount of force per unit area, where you had here for your strain, it's going to be the change in length. So you're changing all over the initial length. And so that is Young's modulus. So we're going to look at an example. So a test specimen with a circular cross region with a circular cross section has an initial gauge length of 500 millimeters and an initial diameter of 60 millimeters. When the instantaneous tensile force in the specimen's 50 kilonewtons, the specimen has a longitudinal elongation of 0.16 millimeters and a lateral decrease in diameter of 0.01505 millimeters. Determine the modulus of elasticity. So here, remember, it's our stress over strain, Young's modulus. And so calculating the modulus of elasticity, looking at Young's modulus, stress over strain, force over area divided by change in length all over initial length. So just rewriting the equation so we can bring up, it's a fraction, denominator divided by denominator. This denominator will move to the numerator. And then in your numerator, the denominator, that fraction is going to move to the actual denominator. So just rewriting it, substituting in what we have. So 50 kilonewtons was our force that we applied. And then the initial length was 500 millimeters. They told us that. And then converting millimeters into just meters to make it all in the same units. Then our area, it was a circular cross section, so pi times r squared, and just changing the radius to be in terms of meters instead of millimeters. Then our change in the actual length, so how much we strained it out, this is the change, and then just changing it into units of meters, solving, and this is what we get for Young's modulus. Now that we talked about that, we're going to get a little bit into the properties of scientific materials. And so in electrical engineering, there's two types of charge carriers. You can have electrons, so we can have electrons here, or we can have holes, which represent an empty space. Either an electron isn't there, so there's one less electron, so it leaves behind an empty space. So they're known as being positively charged. So electrons are negatively charged. They carry a negative charge with them, where holes, it's basically, they're referred to as net positively charged because they're when there's an absence of an electron. So it's referred to as a positive. And so you're going to see these notations used a lot, electrons and holes. And this is referring to the type of doping. So we can either dope with more holes, which refers to p-type. So we have more holes, as you can see here, or we can dope a material with more electrons, which means it's n-type, so it's more negatively charged because there's more of these electrons here. So based on the type of doping, we can either have more holes in a material or more electrons. So we can make a material more positively charged, p-type, or negatively charged, n-type. And so majority versus minority carriers, in a p-type, holes are the majority carriers, but in an n-type, electrons are the majority carriers. And then the minority carriers for p-type are free electrons, where the minority carriers for an n-type are holes. And so we're going to look at the electron band model. And so an electron has energy in discrete amounts, known as quanta. Sort of like quanta levels, like there's energies in specific amounts. So here we see that there's one energy state, here's another energy state at a different level, here's one energy state, and here's another energy state. And so quanta is just states of energy. So higher or lower quanta, higher or lower energy levels. So an electron possesses energy in a discrete amount known as quanta. So quantum of energy is the smallest amount of energy that an electron can receive or use. And so what we're going to see here is we have photons, which is like light. Basically, if we have emission of a photon, it gives off light. When here we have an electron going back down to a lower state of energy. So because it goes to a lower state of energy, it's going to give off that energy it's trying to lose. Where when we have an electron going to a higher state of energy, it requires energy because it has to go to a higher state of energy. So it has to receive energy in order to make it to that higher state of energy. So it absorbs a photon, which is a light particle, and light has energy. And so you can think of the sunlight. It has energy. It can power solar panels. And so the energy in one quantum of light, which is a photon, the energy is referred to basically the energy of a photon is equal to Planck's constant, which this is a constant, multiplied by the frequency. And so this frequency, you're going to notice it's going to be equal to the velocity light divided by the wavelength of light. And so when I refer to velocity of light, that's how fast that waveform is moving. So how fast we're going to, it's propagating. So that waveform is moving. And then the wavelength of light, that's going to refer to what is one wavelength. And so when we have here, what is our wavelength, the actual band of it, And so how long is our waveform? So this actual distance of how long that waveform is, one wavelength. And so one length of the wave. And so when we have our electron bands, which are energy levels, they can only exist at specific energy levels. There's no intermediate. It's quantized. So it's specific energy levels. Electrons feel the lowest energy levels first. And two electrons, they can have the same energy level. So there can be two electrons on each energy level. So here we can have like two electrons, but they have opposite spins. And so that's how you can have two in the same energy level. With one or more quanta of energy provided, electrons can jump to higher energy levels. So say if we have a quantum of light provided, then it receives energy, so this quantum of light, so this electron can jump up to the next quantum. So it can jump upwards to the next one and go there. And so what we're going to see is of course, it would jump to the one right above, but for my drawing purposes, I didn't have enough room to do that because they're really small. So it would jump to the one right above it, that next energy state, the next, if it keeps receiving energy. And so this shows all the energy bands. And so there is n different levels, and there's two, it can store a capacity of twice that amount, because remember, for each level, there can be two electrons with opposite spins. Okay, so energy bands contain n levels and can hold up to 2n electrons, 2 electrons per level. And so first, they're going to start out in the valence band. So valence band are basically filled bands here. And so within your valence band, what's going to happen is your electrons are going to get excited. So they're going to receive energy, and then they're going to jump to the unfilled conduction bands. So that's like when you heat something up, it gets energy. And so those electrons are able to conduct. And so that's what we're going to see happen is the valence band. Remember, it's the outermost shell of the electron. And so it's the filled band in that element. It's filled with electrons. And so it's going to get enough energy to jump to the conduction band. Okay, so band gap. Band gap refers to the amount of energy required for an electron to traverse from the valence band to the conduction band. So the valence band is full of electrons, but the conduction bands, it's open. So it's where electrons want to go, because that's where they get to conduct and can move all around. So it's not filled right now. And so electrons want to jump from the valence band over to the conduction band. But notice insulators, it's harder for electrons to jump. So they can't conduct, which makes sense. In insulators, there's no conduction. It's very hard for electricity to flow through an insulator, such as wood or plastic. Whereas semiconductors, it is easier for electrons to flow. There's a smaller band gap. And then finally, for conductors, there's almost no band gap. So notice that it's the easiest for conductors in order for electrons to flow from the valence band to the conduction band. Now we're going to talk about semiconductors. So semiconductors can either be pure, which is intrinsic, or impure, which is extrinsic. So impurities are caused by dopants. So remember in the beginning, we talked about p-type, which has more holes, or n-type, which has more electrons. P-type material has only 3 valence electrons. So it has one empty spot. It's not at that 4 electrons like silicon. It has 1 less. So it has a hole, such as boron only has 3 valence electrons on the periodic table. Whereas N-type materials have 5 valence electrons. So they have 1 more electron. So you're going to notice that that extra electron is basically going to be moving about. So it's going to be more negatively charged, such as phosphorus. Antimony can also be used for an N-type material. In P-type materials, holes are the majority carriers, where in N-type materials, we have electrons as the majority of carriers. So what we're going to notice is that here in the diagram, notice boron only had 3 valence electrons. it didn't have that fourth one to complete. So when it was sharing with the other ones, there was an empty spot. So this empty spot is referred to as a hole. So it is positively charged, net positive. So p-type, we refer to this when we have holes. And then our n-type here, notice antimony had 5 valence electrons, so that extra electron is just flowing through. So basically, p-types are known as acceptors. They're willing to take an electron to fill this hole. So they would be willing to take an electron in order to take the place of this hole. Where the n-type are willing to give away that electron. They have an extra electron, so they're willing to donate it. So they're referred to as donors. So we often, in times, have our p-n junctions. And so we're going to talk about the p-n junction and why it's important. The p-n junction, basically, as you see right here, it's a layer of p-type material adjacent to a layer of n-type material. So here we had the p-type material, and then it's sandwiched right next to n-type material. Notice that the p-type material has holes as the majority carrier, where the n-type material has electrons as the majority carriers. And so this p-n junction we're going to see down below is going to have a concentration gradient because there's more holes on the p-type side and there's more electrons on the n-type side. So what's going to happen is if you think of a crowded room, people want to go where it's less crowded. So all these holes want to go where it's less crowded and there's less holes. So the holes are going to want to diffuse over to the n-type layer where there's less holes. And so they'll diffuse to the n-type, whereas the electrons here, they're going to want to diffuse to the p-type materials. They're going to diffuse to the left here because there's going to be less electrons. And so they want to go where there's less concentration. And when these holes in electrons start to diffuse, they're going to create a depletion region. So we're going to see below here, when the holes go over to the n-type side, so when the holes actually move over to the n-type side here, we're going to notice that it leaves behind a negative ion when this happens. So when these holes start to diffuse over, negative ions build up on the p-type side because it's losing. Remember how I referred to holes as positive charges? And it's going to have that hole leave. So it's going to leave behind a negative charge, a negative ion, basically. And what we're going to see is when these electrons start to diffuse over onto the p-type side here, it's going to leave behind a positive ion because the n-type material will become more positive because it's getting rid of a negative electron. So it's going to become more positive here. So it's going to leave behind positive ions. And so we're going to get the buildup of ions here at that junction point. And so notice that these ions are what constitute the depletion region. So the negative ions that are caused by the holes diffusing over to the right-hand side into the n-type region. And then we have the positive ions that are created due to the electrons diffusing over into the p-type material. So what happens is the current density can be found by taking the current due to the diffusion. So here we have electrons moving and here we have holes moving. So if you take the diffusion current, so basically how much current is traveling per unit time, so how many of those electrons are traveling per unit time, and divide that by the cross-sectional area, you're going to get the current density. And so what we're going to see is if we're looking specifically, when I say N here, that refers to electrons because they're from the N-type material. So the diffusion of the electrons, so we're talking about the electrons diffusing over to this left-hand side here, is going to be calculated from the charge multiplied by the diffusion constant multiplied by the concentration gradient. And so the concentration gradient, you'll notice that as you traverse in the x direction, so if we go over, because those electrons will be moving over, as they traverse in the x direction, you're going to see that the concentration is going to change. There's a lot of concentration here, where on the p-type side, there's not as much concentration. So there's going to be concentration difference, of course, between the two sides, and that concentration distance depends on how far you traverse over into the other side of the p-n junction. And so in order to simplify our calculation and substitute in a few variables, Einstein created a relationship, which basically has a little rhyme to it. D over mu is equal to KT over Q. So I'll repeat that again. D over mu is equal to KT over Q. So it has like a little rhyme you can think. That's how you'll remember it. And so Einstein's relationship basically relates the diffusion constant D to the other parameters that we can substitute into the equation. So you'll notice that we take our D, so if we move mu over to the other side, we'll get, so if we move this over here, we'll get mu times KT over Q. And so that's what we substituted in for diffusion constant, D. And so that's what you can do in order to simplify the calculation. And then what we can represent is KT over Q is also known as the thermal voltage, which you're going to see there's an electric field that's going to build up because we have positive charges on one side and we have negative charges on the other. And so that's going to create an electric field. And this electric field here will create a voltage. And so this relates to the thermal voltage. So we're going to substitute that into our equation here, because the amount of diffusion, you can have more diffusion if there's if you reach higher temperatures, which we see right here, and you'll have less diffusion if you're at lower temperatures. And so the diffusion current for electrons is indicated with an N. And of course, remember, electrons have a negative charge, negative 1.6 times 10 to the -19th coulomb, where holes, on the other hand, as we see by this equation, have a positive charge of positive 1.6 times 10 to the -19 coulombs. And so instead of using the lowercase n for the electrons, we're going to actually use a lowercase p to represent when we're talking about the whole charge carriers in the p-n junction. So the depletion region, like we talked about, is going to happen because of the diffusion of charge carriers across the p-n junction, which creates an electric field because of the charge difference at the depletion region of positive ions and negative ions. And so the buildup of that electric field is going to create a drift current. And so this drift current is going to oppose the diffusion current. So we're going to see that the diffusion current of electrons, for instance, is going over to the p-type region. But within the electric field, there's a drift current that's going to counteract that diffusion current. So it's going to go in the opposite direction. And that drift current is due to that electric field. And so it's going to be in the opposite direction. And that drift current is going to drift those carriers back over to the side they originally came from. So those electrons will be drifted over to the n-type layer, and those holes will be drifted back over to the p-type layer. And so what we're going to see is that the drift current is due to the electric field. So it makes sense that we're in the equation for the drift current, the electric field is there. And it's going to be the charge times, and then we're going to have this refers specifically n sub n and n sub p referred to our number of electrons or number of holes, respectively. And so mu sub n refers to the mobility of electrons, where mu sub p refers to the mobility of holes. And so a lot of times you're going to notice that the electron mobility is higher than the hole mobility. And we'll see why we like to use this, electrons preferably, more of the time because they're faster. And so our devices can operate quicker if electrons are able to flow at a faster rate than holes. And so when we talk about the total current density, you have to combine the effects of diffusion and drift. So we just substitute both of our equations in here, and then we take out the like terms, we factor those out, and so we can get the total response across the PN junction. And one thing to note is that this drift current is going to build up to equal the diffusion current, so it will reach equilibrium. So then the charge carriers will remain on their sides. So at first, there's a lot of diffusion because of the concentration gradient, but this depletion region's going to grow, and it's going to keep increasing. So it will get bigger and bigger until that drift current is equivalent. So this arrow for the drift current, if we're looking at the electrons, it will be able to cancel out the diffusion current. It will get to the same size, and so that depletion region will grow until that drift current is equivalent to the diffusion current. And at that point is when it reaches equilibrium, and charge carriers will no longer flow across the PN junction. Okay, now that we talked about that, we're going to look at the conduction. So conduction occurs when an electron receives sufficient energy to jump from the valence band to the conduction band. And so here, the electron receives sufficient energy to make the jump, and so it leaves behind a hole. So that's why it looks like an empty state here, is because the electron jumped because there was enough energy, whether it be a photon that gave it enough energy to jump up into that conduction band. And so it creates an electron hole pair when it conducts, because an electron goes up to the conduction band, but it leaves behind a hole. So it's known as electron hole pair generation. And so what we're going to see is the valence band is full of bonded electrons. And so if it receives enough energy, an electron will make the jump to the conduction band, and that will create our electron hole pair. And the conduction band is full of free electrons. But when let's say an electron from the conduction band, when it falls back to the valence band, it's going to emit energy. And so it will give off energy. So we're going to see that. So it must absorb energy to go from the valence band to the conduction band. But if it's going to return to the valence band, it will give off energy. So that's due to the conservation of energy principle. If it drops in energy levels, it must emit energy. Okay, so we're going to look at carrier concentrations. So the pure substrate, what we're talking about, the silicon wafer, it's pure before we dope it. The silicon has approximately 4 outer electrons, and so it's intrinsic. So it just has 4 right now. So our silicon has exactly 4 electrons. And what happens is we dope it. And so notice we're going to dope it with p-type or n-type. Those are the twos we can choose from. And so that's where we're going to introduce either boron or phosphorus. Boron's p-type material, where phosphorus is an n-type material. And so the original concentrations of negative charge carriers, which is referred to as n sub I, and positive charge carriers, which is p sub I, that refers to the intrinsic amount. Those are the intrinsic concentrations. But once you start to dope it with the extrinsic elements, so either 3 electron elements or 5 electron elements, it becomes an extrinsic semiconductors, because the number of charge carriers is increased. So you either have more holes or more electrons. So originally our silicon is intrinsic, and so you refer to the number of electrons and holes with n sub I and p sub I. But then once you start introducing elements with 3 or 5 valence electrons, that's going to create an extrinsic material, because now we're going to either have one extra electron or we're going to have one extra hole. And so that will create an extrinsic semiconductor. Now we're going to look at the equilibrium carrier concentration. So an intrinsic has an equal number of electrons and holes. So for an intrinsic semiconductor, we're going to see the number of electrons is equal to the number of holes. So that's the intrinsic concentration. So what we're going to notice is that for equilibrium carrier concentration, the number of intrinsic holes multiplied by the number of intrinsic electrons, we're going to see is going to be equal to Ni squared. And so Ni squared, it refers to the number of holes and electrons, your intrinsic concentration. Is you have the same amount, so P is equal to N. So P times N would equal Ni squared. Ni represents the number of electrons at that intrinsic concentration. And so you're going to notice that P times N is equal to Ni squared. So you're basically, what I'm talking about here is within an intrinsic semiconductor, the number of electrons is equal to the number of holes. So the intrinsic concentration of electrons, if you multiply that by itself, it's going to equal N times P. It's the same thing as multiplying N times P is equal to one of them times itself. And so that's what we're just trying to say here, is that because they're at the same amount, Pn, it's going to equal Ni squared. So this is the equilibrium carrier concentration, because there's the same amount of holes as electrons for intrinsic semiconductors. And so this equation represents that in a p-type material, you have it can be approximated by the number of acceptor atoms, since those are more dominant. And so the concentration of electrons in a p-type material is remember what we talked about here, the equilibrium charge carrier concentration divided by how many acceptor ions you have. And that will determine how many electrons you must have. Is if you have your intrinsic concentration and you divide it by the number of acceptor ions, number of acceptor atoms, you're going to be left with the number basically of electrons. And for your N-type material, you're going to have mostly donors that are going to want to donate an electron. And so what we're going to see is your concentration in electrons is about how many donor atoms you have, or you can take the product of the intrinsic concentration of holes and electrons and divide that by the number of donor atoms to be left with how many holes you must have. So you can use either method. So the conductivity of a semiconductor is determined by, so sigma represents the conductivity, and it's equal to the charge of an electron multiplied by the mobility, so how fast those electrons can move, times the concentration of those electrons, plus the mobility of the holes, so how fast those holes can move, times the concentration of the holes. So that will determine your total conductivity, and it takes into effect both your electron and your holes in order to determine the total conductivity here. So it takes into account both parts. So here we're going to see silicon is doped with boron, a p-type dopant. And so boron, remember, has basically 3 electrons, and so it's going to have 1 hole, and it's going to have a concentration of 2 times 10 to the 20th carriers per meter cubed, and the intrinsic concentration of electron carriers is 1.5 times 10 to the 16 carriers per meter cubed. So the mobility of electrons is given to us, and the mobility of holes is given to us. So we need to calculate the conductivity. So remember how I talked about you can take what we know is we know the intrinsic concentration and we know the amount of holes, basically our concentration. So what we can do is we can take that intrinsic concentration, square it, and divide it by number of holes in order to find out how many electrons we have. So once we find out how many electrons we have, then we can calculate the conductivity because we'll have been given all the information because we know the charge Q equals 1.6 times 10 negative 19 coulombs. And then we know the mobility of our electrons, the number of electrons we have, plus the mobility of our holes times the number of holes we have to get the total conductivity. Now we're going to talk about the photoelectric effect. And so the photoelectric effect refers to when electrons are emitted when you shine light. So here we're shining a light on this metal surface, and we'll see that electrons are emitted as a result. And so that's what the photoelectric effect describes, the phenomenon of putting a light source on a metal and observing that electrons are ejected. And so the work function is the work required for an electron to leave the surface, and that's how much we'll detail about this effect. So there's defects a lot of times. There's intrinsic and extrinsic defects. And so when we talk about intrinsic defects, there can either be a vacancy, so there's an open spot, or there can be an interstitial. So it's like the same atom with the surrounding atom. So you introduce another one, but it's the same as all the others around it. So it matches. Extrinsic point defects are when we have a foreign atom. So you'll see here, when we have a substitutional foreign atom to fill that vacancy, it's not like the ones around it. Or when we have an interstitial foreign atom, you're going to notice that it does not match its surrounding ones. And so those that are basically either substituting or going in between, and it does not match the ones around it, it's extrinsic for the defect it will cause. Where the intrinsic is the same one, or it's just like a vacancy left behind. So those are the two different types of defects you'll have within your crystals. So they can either be point, line, area. So there's different types of defects that we can have within our crystals. Now we're going to look at the diffusion coefficient. And so for the diffusion coefficient, it's the rate of diffusion of an amount of substance from high concentration to a low concentration. So just like we saw at the p-n junction, those holes going across from our p-type to the n-type, because of that difference, we're going to see the rate of diffusion. It's going to be determined by the diffusion, the proportionality constant, multiplied by e to negative q all over the universal gas constant times the temperature. And so what we're going to notice here is that diffusion coefficient can be calculated in order to determine how fast that diffusion is happening between our p and our n-type materials. So to go from one side over to the other, how fast that diffusion process is. And so that's just relating back to how we had our diffusion coefficients. So this is the actual equation you can use to calculate it if you know these parameters. So if given the activation energy and you actually know the specific temperature and you are given your universal gas constant, then you can plug in that information to find your diffusion coefficient and get the result in order to plug in and find out how fast that diffusion is actually occurring within the p-n junction. So now that we talked about like all the stuff that's happening in our devices for semiconductors, we're going to look more now into the practical applications. And so from the basis of everything, we have atoms. atoms build all living things that we see today. And so they're the building blocks and the foundation of our major. They're the subatomic particles. And so they consist of three particles. Atoms have protons, which have positive charges, as we see in the nucleus of the atom, neutrons, which have neutral charges, as seen in the nucleus of the atom, and electrons, which are outside the nucleus of the atom. And so protons are positive, neutrons are neutral, electrons are negatively charged. And so what we're going to notice is when we talk about positively charged, we have more protons than electrons. If we talk about negatively charged, we have more electrons than protons. And if we talk about it being neutral charge, the amount of protons must equal the amount of electrons. A charge is measured in units of coulombs, and the charge of an electron is negative 1.602 times 10 to the negative 19 coulomb. The charge of a proton is exactly the same, but opposite signs since it's positively charged, and a neutron has approximately 0 charge. And so if we're talking about the size of an object being insignificant compared to the distances involved, the object is oftentimes referred to as a point charge because it's so small compared to everything around it. We don't take into account like the actual shape of the particle. We just say it's a point charge. So when we refer to point charges, we're just saying it's so small compared to its surroundings. So now we're going to talk about current. So current is the flow of electrons. And so it's the amount of charges that pass through a cross-sectional area per unit time. And so the amount of charges here that pass through this cross-sectional area, we see that there are 4 charges passing through this cross-sectional area. And so current is defined as the amount of charge per unit time. And so that makes sense, just like we see here. And it is given in units of amps. And so what we're going to notice is by convention, current is going to flow from the positive terminal of the battery to the negative terminal of the battery. And so let's look at an example. It says determine the amount of charge delivered by the circuit after 10 seconds. The current in the circuit is given by half the time the current has been running through the circuit. Assume no initial current flowing through the circuit. Okay, so we know current is equal to the amount of charge per unit time. So just rewriting the equation, if we multiply dt to the other side, and then we know current's been running through the circuit for about half the time. So that's why I said t over 2 here for the current. And what we're going to do is if you take the integral, because we have to determine how much charge is flowing through the circuit. And so if we take the integral in order to solve the equation, in order to solve in terms of our charge, you're going to take it from 0 to 10 because there was no initial current. So we're starting at time 0 and going up to 10 seconds. And so here, what we're going to see here is when we take the integral and get it in terms of charge, we're going to find out that there was approximately 25 coulombs of current that ran through the circuit. Basically, we had 25 coulombs of charge. And now that we saw a practical application, we're going to look a little into the electric fields. And so the electric field from a line charge. And so when we talk about this, it's basically when we have here our electric field, it's going to be created by the line charge density all over 2 pi times the permittivity times the line of charge. And so what we're going to notice is that if we have just our line charge here, what we're going to see is that our line charge density, our electric field, basically, if we look at it, the electric field is emitting from this line charge. So we have our line charge that is basically here along a line in its charge, and we just assume a positive test charge, and then it's going to the right and left. It's going away from this line charge. And so R is the line of charge, and A of R in this equation refers to the unit vector, normal to the line of charge. And so that'd be perpendicular to this line of charge here. And so that's why we see our R here is perpendicular to this line of charge. And so that's the electric field that is coming from a line of charge. And what we do a lot of times to determine the electric field is we place a positive charge, and then we know that the electric field emits from a positive charge. And so that's how we're able to draw it. And now we're going to look at the electric field from a sheet charge. So if the sheet is charged, it's going to emit the electric field basically. So we see arrows going out in both sides because it's emitting this electric field. And so we're going to see that our rho sub S refers to the sheet charge density. And so that's the total charge divided by the total area. And epsilon here represents our permittivity. Then we have A sub Z, which represents the unit vector normal to the sheet. So it's very similar to the electric field from a line charge. Now we're just working with a sheet. So we have area involved. And so let's look at an example. It says calculate the electric field 5 centimeters away from the center of a metal sheet with dimensions 15 by 15. So if you want to think about it, basically we have a metal sheet with dimensions of 15 centimeters by 15 centimeters. And so we know the total charge, which is 24 microcoulombs, but it's talking about the electric field 5 centimeters away. So if we're talking about 5 centimeters away, I'm going to say that's like about this distance here, 5 centimeters. And so here we have an electron. I'm sorry, a positive test charge, because we put positive test charge, so we're actually going to have a proton. And so here if we're calculating it, our charge is 24 microcoulombs divided by our area. And so we did the length, and then we just changed it in terms of meters and then squared it to get the area. And so just plugging that into our equation, and then knowing our epsilon and your unit vector has unit of 1 because we're just finding the magnitude right now, you're able to calculate the electric field, which is in terms of newtons per coulomb, or it can also be given in terms of volts per meter. Okay, now voltage is a measure of electric difference between 2 points. So right here, we're going to see it's the amount of work per unit charge. And so work is given in units of joules, and then charge is given in units of coulombs. So voltage is represented by volts, but can also be given in terms of joules per coulomb. So right here, what we're going to notice is there's a potential difference. This plate on top is positively charged, where the plate on bottom is negatively charged. So there's a separation of charge, and there's a potential difference. One's positive and one's negative. So one's higher up in potential than the other. So there's a voltage between those two levels. As we see here, there's a voltage between the two plates. Okay, now that we talked about that, the electric field from two parallel plates can be given by the voltage divided by the distance between those two plates here. So the electric field, we notice, goes from positive to negative charge, and it is representative of the voltage divided by the distance. And so you can actually calculate how much voltage is stored across those two plates if you know the electric field and the distance between those two plates. And so it says, for an example, calculate the electric field strength between two plates separated by 0.5 meters that are connected across 500 volts. So if we know we have 500 volts and there's 0.5 meters between those two plates, then our electric field is going to be approximately 1,000 volts per meter. I could have also written 1,000, just like we saw over here, in terms of, I think it was newtons per coulomb. So I could have used those for units as well. Either one is acceptable. Now, we discussed resistance earlier in the lecture, and we're going to see it apply to the series circuit. So a series circuit refers to all the components which we see here are in series. So there's only one path to go from the start to the finish. So we started at the battery and we just went through and we ended at the same point. And so here within our circuit, there's only one path to flow through. So for series circuits, because there's only one path, you add all the resistors in series. And so resistors, just like we talked about, they're circuit components that resist the flow of electricity. So they slow down our current. And so our resistors here, we have 3, R1, R2, and R3, each with different values. So 3,000 ohms for R1, 10,000 for R2, and 5,000 for R3. And to find the total resistance, you add all them together. And so you add all 3 resistors to get the total resistance. So here it would be 3K plus 10K plus 5K to give you 18K. And so that would be your total resistance. Now we're going to look at a parallel circuit. And so in a parallel circuit, instead of all components having the same current as in a series circuit, components in parallel have the same voltage. So they're all going to have the same voltage difference across them. And so that's what we're going to see here is within the parallel circuit, notice that they're attached in parallel with one another. So they share the same node. And so here they share the same point on top as on bottom. And so resistors 1, 2, and 3 are in parallel. They share the same point above. They're all connected. If you look here, before you come to an element, they're all connected to the same top node as well as bottom node here. And so that's what we're able to say, that these resistors are in parallel with one another. And therefore, they're going to have the same voltage drop across each of them. So for resistors in parallel, you can use the equation 1 over the resistor 1 plus 1 over resistor 2 plus 1 over resistor 3 to get the total resistance. Or you can do 2 at a time, and it turns into an easier equation. So you can first do R1 times R2 all over R1 plus R2 to get the equivalent resistor here. So we could call this R equivalent 1. And then you could do R equivalent 1 times R3 all over R equivalent 1 plus R3 to get the total equivalent. So you can work 2 at a time for those in parallel and then get the total equivalent resistance of the circuit. And so now that we talked about that, we're going to look at an example. And for this example, it has to find the equivalent resistance. So the biggest tip is to start furthest from the source. So I'm going to start, my source is over here, so I'm going to start on the right-hand side, and I'm going to combine these 2 resistors right here. And they're in series with one another because they only share one node. So R2 plus R4 is going to be 9 ohms. So here, my R2 plus R4, 3 plus 6 ohms, that gives me 9 ohms. Then I'm going to, so I found an equivalent resistor here. So I'm going to do the next step, and this 18 ohm is going to be in parallel with these 2 I combined together. And so that's why I did the 2 combined together in parallel with 18. So it's going to be 9 in parallel with 18. So I did the equation here, and I got 6 ohms. And then lastly, after I got the equivalent resistor, for that segment, I'm going to notice that I add R1 in order to get my total resistance. And so that's how I was able to go piece by piece from the furthest and work my way back to the source. So that's why I added R1 at the end. So I added 4 ohms, and that's how I got the equivalent resistance of 10 ohms for the entire circuit. So I started furthest from the source, and I combined resistors in series and in parallel, and then was able to work my way over. And now we're going to talk about Joule's law, which is the conversion of electrical energy into heat energy by the resistance in a circuit. So a resistor, remember how I said that it limits the current flow? Well, it's able to limit the current flow by giving off that energy as heat. So your resistors dissipate that as heat. So we're going to notice within Joule's law is that it uses the resistance. So the resistance times the current squared is going to be give you the amount of power that is going to be absorbed by the resistor. And so you can also write it as V squared over R or IV. What they do here is they just substitute basically in the main equation is IV, and they use Ohm's law, which says that voltage is equal to current times resistance, and they substitute in for current. It's equal to, if you just solve for the current here, it's V divided by R. And so they substituted in for current in order to get this equation here, or they substituted in for voltage. If you just substitute for voltage, it's I times R. And so they're able to write it in this equation here by substituting for the voltage. So you can see how power equals I times V. You can derive the other two equations by just using Ohm's law. Now that we talked about that, we're going to look at an example which asks to find the power dissipated by a 100 ohm resistor that has a current of 5 milliamps. And so here we have the current, we square it and then multiply it by the resistance to get the total power. Notice that power is in units of watts. Now we're going to calculate the conductivity. So the conductance, which is in the symbol for conductance is G, is the opposite of resistance. So instead of, remember how we talked about ohms for resistance? It's backwards. It's in terms of mhos because it's the exact opposite. Or Siemens, either one you can use for the units. And so instead of an impeding current flow, it refers to the ease of current flow. And so it's the reciprocal of resistance. So that's what we see here. Conductance just refers to the ease of current flow. Okay, now we're going to talk about two main components within electrical engineering, inductors and capacitors. And so an inductor refers to a coil. So we have a coil here. Notice we have a coil. And so this coil is going to have a current pass through it in order to produce a magnetic field. And so you'll see these magnetic field lines. If we pass a current through this coil, so right here, if we pass in a current, so call this I, and it's going through the coils, it's going to create magnetic field lines that are going to go from one end to the other. And so these magnetic field lines are going to store energy in them. And so these basically magnetic field lines are created for an inductor when you pass a current through it. So when you pass a current through an inductor, it's going to create a magnetic field. And so an inductor behaves as a short circuit once you get a constant current. And so the relationship for voltage in an inductor is given by voltage is equal to the inductance times the derivative of the current. So if you pass a constant current, then it's not going to be changing. So this would go to 0 and you would have 0 voltage across the inductor. So it would behave like a short because there would be no voltage drop across it. So current would just pass through. And so inductance is measured in units of henries, just so you know. And so for inductors, if you want to derive the current, what you can do is you can rewrite the voltage in an inductor, multiply both sides by dt, and divide both sides by L in order to just get di on one side. And then if you take the integral of both sides, what you're going to notice is that you can rewrite it so that you get the current at time t minus the initial starting current. And you can solve and get the equation now in terms of your current at any time for the inductor. And so what we see here is we're able to see the first two equations for the inductor. For power for an inductor, remember, power is equal to I times V. So we can plug in what we know for V, which is L times di dt. So we just did that here. The work in an inductor is given by 1/2 the inductance times the current squared. Inductors behave just like resistors. You you sum together inductors in series, so one after another. You add them just like resistors. Inductors in parallel, you treat them just like resistors in parallel. You do 1 over L1 plus 1 over L2 plus how many inductors you have. And so we're going to look at an example here. And so a current source produces 0 amps for time less than 0. And then we have this equation for time greater than or equal to 0. And so the voltage in inductor is given by, we know here, our inductance, well, our inductor in the equation is 4 millihenries. And so the derivative of the current. So we were given the current. So by taking the derivative of this, we're able to solve for the voltage for the inductor. Now, we want to know the voltage at time 0. So we're going to plug in for t here, 0. And so by plugging in 0, we're going to get that the initial voltage on the inductor was 28.8 volts. Now we're going to look at capacitors. So capacitors store energy between their two parallel plates. So remember how I said there was a potential difference between the two plates? There's positive charge and negative charge, and an electric field is created. So a capacitor stores energy in its electric field. And so what we're going to see is the equation for a capacitor is given by I equals C times the derivative of voltage. And so if we have a constant voltage, then this would go to 0 because it wouldn't be changing. So we would have 0 current. So if it has 0 current, then it would behave like a open circuit because no current could pass through. And so that's why we refer to capacitors act as open circuits if you have a constant voltage. So if we know the current for a capacitor, we can derive it the same way to get for an equation relating the voltage in a capacitor. So we multiply both sides by dt, divide both sides by c, and then we take the integral, and we're able to get the voltage at any time minus the initial voltage. In rearranging the equation, we'll get it in terms of the voltage at any time for a capacitor. And so we reviewed the two first equations for the current and voltage in a capacitor, but looking at the power in a capacitor, I times V is equal to the power. And so substituting in for I, C times dV dt, which we saw, that's our relationship. You can find the power, and you can also find the work done by a capacitor, which is equal to 1/2 the capacitance times the voltage squared. Notice, though, capacitors behave opposite of resistors. Capacitors in series add like resistors in parallel, where capacitors in parallel add like resistors in series. So inductors behave more similar to resistors, and since you can add them together just like resistors in series, but capacitors, on the opposite hand, they behave like resistors in parallel when they're in series, and they behave like resistors in series when they're in parallel. So note the difference. So here, we're going to look at the current in a 0.6 microfarad capacitor is 0 amps for time less than 0, and 3 cosine 50,000 t for time greater than 0. So we need to find the maximum power delivered to the capacitor. And so here, we wrote out the current, and we know the voltage in a capacitor is equal to this equation. So plugging in our capacitance and our current, we're able to solve this formula to find the voltage in the capacitor at any time. So now in order to determine the power, remember power is equal to current times voltage, and we know current is the capacitance times the derivative of voltage. So here, plugging in our current, and then plugging in, because we know our current up here, 3 cosine 50,000 t, then we were able to find our voltage actually. So plugging that in, we are able to rewrite and simplify our result. And then using a trigonometric identity, we were able to turn our formula, because this is a cosine times a sine, and express it in terms of only one trigonometric function. And by graphing this, we see that the peak is at 150. So that's when the maximum power occurs, at 150 watts. Now we're going to look at reactance. And so what we're going to talk about right now, right before, is DC current. And DC current provides a constant current or voltage. And so you're going to see here, it would either be a constant current or voltage. So let's just say this is like 5 volts DC. And so that's what we have right here for our voltage. It remains constant throughout time. It does not change. Where alternating current, on the other hand, is going to change with time. And so we're going to see for alternating current, it's alternating current or voltage, but it usually looks like a sinusoid. And so it can go up to 5 volts and down to -5 volts, let's say. And so notice that alternating current, it varies with time, where direct current does not change with time. And so in AC circuits, energy is either stored or released by capacitors and inductors. Remember, capacitors store energy in their electric field, whereas inductors store energy in their magnetic field. And so this energy is known as reactive energy, and it's the time rate of reactive energy is known as reactive power. And so the magnitude is known as the reactance. So reactance is often symbolized with capital X. And so we can have capacitive reactance. So that would be capital X sub C, or we can have inductive reactance, which is X sub L. And so those are the two we often talk about. So capacitive reactance in general refers to opposition to current flow in an AC circuit. And so it varies with frequency. So take that into account, that it's dependent upon the frequency, how much opposition it will have. So the capacitive reactance is the opposition to current flow in a capacitor, whereas inductive reactance refers to opposition to current flow in an inductor. And so the formulas that you're going to see over and over again for a capacitive reactance is X sub C, which represents the capacitive reactance, is equal to -1 over omega C, where the inductive reactance X sub L is equal to omega times L. Omega is your angular frequency given by 2 pi times the natural frequency. And so using these equations, you will be able to find the appropriate reactance based on the capacitors and the inductors you have within the circuit. And now we're going to talk about impedance. So I think impedance, the best way to look at it is it's an umbrella term. So impedance incorporates reactance and resistance, because with any circuit, you have resistors and you have inductors and capacitors. And so we saw that inductors and capacitors have reactance. So this is where we have our inductors, which are symbolized with L, and capacitors, where resistance is with our resistors. Just R represents our resistors. So impedance is an umbrella term that incorporates both reactance and resistance. It's a combination of both. So it can either be written in our rectangular form, where we have resistance, our real part, and our reactance, which is our imaginary part. And so impedance is a complex quantity made up of both the real part of resistance and imaginary part reactance. So it can be expressed in polar form, not only rectangular form. So you can take this quantity and convert it over to this format here using your trigonometric skills. And so talking about impedance, we just said that's the resistance combined with the reactance. And so notice that the impedance of a resistor, it's real, so it has no imaginary component. It doesn't have the J imaginary term here. So recall J is equal to, you should know this from math. You might have seen it as I. It's equal to the square root of -1. In electrical engineering, though, we don't use I because it gets confused with current. So we use a J instead. But notice that the resistance, the impedance of a resistor is just R. but the impedance of a capacitor, it's going to be J x c, which is going to be substituting for x of c, our negative 1 over omega c. The impedance by an inductor is J x of L, which substituting in for x of L, you're going to get omega L. And so now that we looked at that, we're going to look at impedance in Ohm's law. So Ohm's law for DC circuits basically relates the voltage is equal to the current times the resistance. And so you can rewrite this in terms of current if you just divide by resistance on both sides, or you can rewrite it in terms of resistance if you divide by current on both sides. For AC circuits, it's the same thing, but instead of saying resistance, we're now working with capacitors and inductors, so we put impedance. But because impedance can be a complex quantity, we use the bold notation. And so notice that voltage, current, and impedance in these equations are all bolded because they'll have a real and imaginary component. Now that we talked about that, let's look at one example. And so this example involves a sinusoidal source. And notice that we have inductors and capacitors. So we know we're going to be dealing with impedance because we'll have both resistive elements and capacitive and inductive elements. And so looking at our resistor, we have a 10 ohm resistor. Looking at our capacitor, calculating the impedance, negative J 1 over omega C. See that our frequency of our source is 50 hertz, so I plug that in for frequency. And notice that our capacitance is 180 microfarads. And so I just plug that into the equation to get my impedance by the capacitor. And then I did the same thing, get my impedance by the inductor. And looking at this circuit, you have to recall that if we want to calculate the current basically through the resistor and inductor, what we're going to do is we're going to take the voltage across the resistor and inductor and divide that by the impedance. So remember, the resistor and inductor, if you look at it, is in parallel with the capacitor, which is in parallel with the source. And so all three have the same voltage or potential difference across them. And so we can substitute in the voltage across the resistor and inductor here is going to be 100 volts AC. And so here we're going to write 100. And then there was no phase angle given. If they did give you a phase angle, it would say something like 30 degrees or something. So they gave us no phase angle. So we're assuming that our phase angle of our source is 0 degrees. And then our total impedance is going to be the resistor plus the impedance of the inductor. And so that's what we did here. For our impedance across that branch, it was the resistor, which was 10 ohms, plus the impedance of the inductor. And so taking that voltage, if you remember your polar, the magnitudes are going to divide. So 100 divided by 14.404. And the phase angles are going to subtract. So it's going to be 0 minus what's in the denominator. And so that's what you're going to do in order to find the total current flowing through your resistor and inductor. So the last term is admittance, which refers to the reciprocal of impedance and is denoted with a Y. And so admittance is a complex number because it's the reciprocal of the impedance, which is also a complex number. And what we're going to see is it has a real part, which remember how we talked about resistance for impedance? For impedance, it was equal to the resistance plus or minus J, and then it was the reactance. Well, here the reciprocal of impedance is admittance. The reciprocal of resistance is conductance, and the reciprocal of reactance is susceptance. So we just rewrote the entire equation for impedance, but in terms of the reciprocals. So 1 over Z, 1 over R, and 1 over X. And so that's what we did here. Now, giving a whole overview, the three most common components you're going to find within electrical engineering are resistors, capacitors, and inductors. And so looking at the impedance, a resistor has an impedance of R, a capacitor has an impedance of negative J over omega C, and an inductor has an impedance of J omega L. And so when we talk about these, capacitors and inductors have reactance, but resistors don't. They have the same value. They have a real part. They have no imaginary part. The reciprocal of resistance is inductance. The reciprocal of the reactance, if you take the reciprocal of this, you will get J omega C. Take the reciprocal of this, you'll get negative 1 over omega L times J. And so susceptance is the reciprocal of reactance. So that's what you'll get here. And this table just clearly illustrates the relationships between those three. And those are the biggest three components that you will see throughout your entire electrical engineering career. And then here's just all the references that were used in order to help make this section specifically on the material science. Thank you.